Is it okay now? Better?
Yes, sir.
Background noise.
But there is some background sound.
Now?
Yeah, okay.
Yeah.
Yes, sir.
Okay, so today we are going to revise week 10 and 11, which is basically the graph theory part. Okay. So I will try to finish it in first 1.5 hour. Most important things which are required for endum or it might gain you marks in endum, we are going to revise that first. And later many of you have asked for an extra session regarding week 11. So we will look into that week 11 in this particular session also. So this session is of 3 hours. And in that first 1.5 hour to 2 hours, we are going to revise the most important topics which are pretty much important for your end-term preparation. And then the final 1 hour, I will dedicate it to the algorithms, week 11, whatever the algorithms, spanning trees, everything. Clear?
Yes, sir.
Yes, sir.
Yeah.
So, if possible, can you also help us with week 7, 8, and 9? Anything which is very important?
Yes, sir.
Okay, if there is time, we will cover. Okay, I have many important topics in graph theory. Maybe don't laugh like these are the only topics are there. But yeah, so I have
Sir,
removed.
please cover algorithm part.
Hmm?
Sir, algorithm part.
See, yeah, as I already said, I will cover the most important topics first and later I will cover the algorithm part. So if it is important, I will cover it in the revision session only. Okay. If I didn't discuss,
Okay,
if
sir.
you want the discussion on it, we can have that discussion in the last 1 hour. Okay. Can I have everyone be on mute so that I don't get an echo? So if you have doubt, you can unmute and ask the questions. If you don't have, kindly mute yourself so that each and every minute will be effective for us. Okay. Yeah. Let us
So our
start now.
main focus will be on week 10 and 11 today, right?
Right. So already there are,
Okay.
we have 2 revision sessions already done.
Yes,
So
sir.
they have covered till week 9, I hope.
Yes, sir.
So
Okay.
today we are going to cover, today we are going to start with week 10, which is basically the basic graph theory, and week 11, advanced graph theory. So both of them things we will cover. And these are the most important topics I have come with. So other topics you go through or not is not important, but you must go through these all topics which I am covering today.
Sir, yesterday, I think day before yesterday's session, Subhashi sir didn't discuss about the local maxima and minima. So, are these topic important?
I see if he didn't discuss, then it is not that important for your end.
Okay, okay.
Okay. Yeah. So today we will start with the basic things, like we start with seeing what is degree of a vertex, and then we look at vertex coloring, vertex cover. What are these things? These terminologies we will understand, and we will cover what is an adjacency matrix and how we draw an graph using adjacency matrix, or if a graph is given. So this is actually another way, another representation of a graph, adjacency matrices. So when an adjacency matrix is given, how to draw the graph, and when a graph is given, how to write an adjacency matrix. So we'll look into that also, and later we will go and see what is BFS and DFS. In particular, how to predict original graph, when a BFS or a DFS is given to us. So there is a question in mock also, I guess. So you might expect one question or may not, it may not come or it might come. But this is important. So how to predict, we will see that. And later we will see forward, backward. What are these forward edges, backward edges and cross edges? How many number of forward edges are there? How many number of backward edges are there and cross edges are there in a particular DFS tree? Once you compute DFS, then we can compute this forward, backward and cross edges. And after that, we will look into DAGs and topological sortings and longest path on the DAG. And after that, we will go and see the algorithms and we will understand when can one algorithm be applicable. So right now I wanted to cover this first, and then I will cover trees and minimum cost spanning trees. Okay, and in minimum cost spanning trees, we know there are only two methods. One is prims and one is Kruskals. So we expect you to know at least one of the algorithm. If you know both, it is good. Okay, so what we expect is you should know at least one algorithm so that you can compute the minimum cost spanning tree. Okay, so let us start with the first topic, which we have is the degree of a vertex. So a degree of a vertex in a given graph G, so in a given undirected graph G. So this particular term degree refers to an undirected graph. Okay, so in a given undirected graph G, the number of edges that are incident to vertex I. Incident means neighbors, or which shares an edge with this vertex I. So the other vertices which shares a direct edge with vertex I. So those vertex are called, sorry, those edges are called incident, which are connected to vertex I. So it's not neighbor, sorry. So incident, adjacent, both are different. Okay, incident means we refer with edge and a vertex. So one edge is incident to one vertex means that particular edge has one of the end as vertex I. So this is an edge and this is vertex I. So this particular edge is incident to vertex I. Okay, and if I have any other vertex j here, now j is adjacent to I. So the difference between incident and adjacent is that. So we have to count the number of edges which are incident to this vertex I. So that particular number of edges, when you count, if you get some number, that particular number is called the degree of a vertex. So I hope this is very clear to everyone. So if we take any example also, so what is the degree of B now?
Three.
Three.
Sorry.
Three. So there are three edges
Three.
incident to vertex B. So the degree of vertex B is 3. Similarly,
Sir,
vertex A is
One.
1,
D,
2, 2,
and 2.
2.
So this is what the degree of vertex is. So
If
in an
direct,
undirected graph. Yeah. Any doubt?
no, sir, got it.
Got it? Yeah. But when it comes
Sir,
to
what about directed graph?
yeah, so what about directed graph? So if it is directed graph, if it is a directed graph G, then we have for each vertex we have in degree and out degree.
And out there. Okay.
So there will not be any degree anymore. So degree will be only for undirected graphs. And for directed graphs, we have two numbers now. Not one number, we have two numbers. And in degree means the number of edges that are coming towards that vertex I. So for example, let us take this only with directions. So this is a directed graph. Okay. So if I wanted to compute the in degree of vertex B, maybe. So I have to look at number of edges that are coming towards B. So towards B, the direction is towards B.
2.
So in degree of vertex
Two.
B is 2. Similarly, in degree of vertex D is, so there are two edges that are coming towards D. So even the in degree of vertex D is also 2. And out degree is number of edges that are going away from D. So starting from that vertex. So you can see here, if I see from, if I wanted to compute the out degree of this vertex D, I have to look for edges that are going outside or it is pointing opposite to it. So are there any edges that are going
No, no, sir.
right? So therefore, the out
You?
degree of this vertex D is, out degree of this D is 0. But you see here, for vertex B, in degree of B is 2, we have seen that. Also there will be out degree of B.
1.
1. Think about it.
No,
Is it 1?
2.
Yeah. So there are
Sorry,
two
2, 2.
edges
Yes, yes.
2, sir.
that are going away from B. Okay. So therefore the out degree of B will be 2. So remember, for directed graph, we will have in degree and out degree separately. So 2 numbers will be associated to each of the vertices. If it is undirected graph, then there will be only one term called degree of a vertex, which is the number of edges that are incident to that particular vertex is what degree of a vertex means. Okay.
Sir, I have one doubt here. Suppose any directed graph. For undirected graph, all the vertices of graph should be connected. Means either ways, right? Both the ways. Suppose in directed graph, you can see A, B connected in both ways, but B and D only one way. So it is directed graph, right? And in case of undirected graph, all the vertices should be connected to each other, right? Means not
All
connected to each other.
All the edges have bidirection.
Bidirection. Yes,
Correct.
yes.
So all the edges have bidirection. So if all the edges have a bidirection, then that graph is an undirected graph. And
sir, in exam, if it is not mentioned in question that if it is mentioned on the graph and upon looking on the diagram, so suppose there is only simple line between A and B, between vertices, so we can consider it as undirected graph, right?
Yeah, correct.
Okay. Thank you.
Okay. Now
Sir,
let us come.
Sir, I had just one simple doubt. There are some graphs, there are question in activities also. The graph was undirected, means there are both side arrows, but one side there was only one arrow. Just as we can consider A to B has the double-sided arrow and B to C has also D to C is, but from B to D there is only outgoing vertex.
Okay.
So that graph would be called undirected or directed?
Directed. That is an undirected. So even if you have one particular edge which has only one direction, the whole graph will become a directed graph.
Otherwise, for being undirected, every vertex should be there, and for being directed, only one vertex which should be directed, we can call it direct.
Edge, not the vertex, edge.
Edge.
Correct.
Okay. Thanks.
So number of edges are 4, right? In the above example you gave, or 8?
Which one?
This undirected graph ABCD.
The
number of edges will be counted as 4, right?
Yeah, only 4. So we don't count 2 directions as. So in an
count only once, right?
Yeah, only once. You will count it only once. So that is why, in order to not have more confusion, we don't give directions to an undirected graph. So we will count this particular edge as once only. So this is one edge, this is another edge, this is one more edge, and this is one more edge. So there are 4 edges and 4 vertices in this graph. So this graph is undirected graph with 4 vertices and 4 edges.
Okay, sir.
Okay, so that is what it is. Okay, so let us come. I don't think we should spend much time on degree. So that is the main takeaway. Main takeaway is this. So what exactly is the degree you should know in a graph? What exactly is degree that you should know?
Sir, in the directed graph, will we consider the double arrows as 2 edges or just 1 edge?
See, in directed graph, we don't talk number of edges basically.
Okay, sir.
So if we wanted to talk, then you will, in a directed graph, we will consider it as 2 different edges, but that is out of topic. So we don't want that, or we didn't study properties on edges of a directed graph, right?
Okay, sir.
Nothing like that. Okay, don't worry about it. Okay, let us come to graph coloring quickly. So graph coloring or vertex coloring or simply coloring, everything means the same. Okay, so graph coloring or vertex coloring or coloring. So all these 3 refers to what it means is, simply it means you have to find the minimum number of colors. So let's say color 1, color 2, we cannot take the red, blue, yellow, orange in the exam. So you can treat it like color 1, color 2, color 3. And what we have to do is, we have to find a minimum number of colors that are required to color every vertex with one color, one particular color, such that no two adjacent vertices have same color. See, you have seen adjacent here. So adjacency is between vertex and vertex, and incidence is between edge and vertex. Okay, so no two adjacent means neighbors. So if you have a neighboring vertices, those two vertices should not have the same color. So like that, I have to color my whole graph, all the vertices in my graph with minimum colors. So that is what graph coloring means. So the vertex coloring or the coloring means. So simply if you take this example, so this is a graph with 8 vertices and some number of edges we have. We have to color this graph. Okay. So what is the approach and how do we start first?
We start any random color. After that, we can leave the choose different color which vertex are connected to edge.
Yeah. Okay.
Sir, we take the vertex which has more number of edges.
Okay, that is also one method. For coloring, it might not affect that much, but for vertex cover, it might affect. So there you have to be very cautious. Choose the maximum number of edges connected vertex. Here also, it is better to choose the maximum connected. If you don't wish to choose like that, then you better start with one vertex. So here A is there. So I will start with A. So I will color A with one color. Okay, let's say green is my first color or color 1. Okay, so this color I will try to give this particular color to maximum number of vertices possible. So if I give green color to vertex A, I cannot give green color to vertex B because that is the condition we have. So B is an adjacent vertex to A, so I cannot give the same color to B. Similarly, for C is also an adjacent vertex, and also H is also an adjacent vertex. So A, B, C, if you want to go alphabetical order, so now D you should give green color. So once I give this same color to vertex D, now I will be, so some vertices will go off, like F and E cannot have green color. So B cannot have, C cannot have, F, E, H cannot have, but G can have the same color. So try to give maximum possible vertices the first color. So this is the maximum. I can only give three vertices the first color. So now what I do is I will take the color 2, or now I just take color red and I will start coloring. So I will start with B. So once I give red color to B, what happens is I will look for the adjacent vertices that cannot be taken red color. So yeah, so B to F, F cannot take red, and C can also cannot take red. So hey, E can take red, right?
Yes, sir. Here we can give to H, sir, right?
You can see if you don't wish to give to E, you can give to H. Okay. So now you see you cannot give any red color to any of the remaining vertices. So E, C, F cannot be given the red color, cannot be given the green color. So now we have to take the new color. So maybe some gray. So see, if I give C the gray color, then I cannot give the gray color to E. So therefore I have to choose F. I can give gray color. Now you see, for E, I cannot give red color, I cannot give green color, I cannot give gray color. So therefore I have to take a new color for E. Maybe some light blue. So this is how we do the coloring. So what is the graph coloring or vertex coloring for this?
4, sir.
4. So this is a 4 coloring graph. So this particular graph is a 4 coloring. Okay, this is how we do the graph coloring. So this is also clear, I guess. So we have done these things in the past, and now also we are revising.
It's a non-planar graph because edges are crossing, right?
This is a non-planar graph maybe, or you can just pull out D and E outside, then maybe it will be a planar.
Sir, so when you were first doing this exercise, you didn't color E red, right? Why was that?
No, you can color E with red. So someone said, why can't I color H red? So I just replaced the E with H. That's it.
Okay.
Even though whatever coloring you do, you will get the 4 colors. So the colors are not important, but the number of colors required is the important thing.
Got it.
Okay.
Sir, one doubt here. The 4 coloring graph. So we means in the video also said that 4 colors max we can give.
That is for.
So is it a theorem or it is right now for max one? Is it out of scope?
Right now it is out of scope only, but for planar only. Planar, for any planar graph, so you can take. We will take max of 4 colors.
Okay.
Okay. So that is.
So more than 4 colors are possible, right?
More than 4 colors are possible for non-planar graphs. Okay. So this is a small theorem in graph theory. Okay. So if it is a planar, not a small theorem, it is actually called 4 coloring theorem. It's a big new invention, recent times invention in graph theory. So previously it was 5, then recently it was proved that 4 colors is enough. But the proof is very complicated and we don't deal with that.
So can you explain just what is planar? Planar means in a simple line. That's
okay. So how many of you know planar graph?
Sir.
Yes, sir. Okay. So what planar graph means is a graph you can draw in such a way that no two edges cut or cut edge.
No two edges cut each other.
Yeah, like this. So like this. So there will not be any intersection in between. Okay. And
they're not understood. Intersection means that here.
See, this is one edge is going like this, E to H, and F to G. This is one more edge, and these two are intersecting here. If the edges are like this, then it is non-planar.
Okay. So this graph is non-planar, right?
This graph is non-planar.
Suppose we remove all this D, E, and this BC and FG. So this will be planar graph.
Okay. So,
sir, but we can make the B to C connection
out of
from over A.
Even if you do that, finally what happens is from A to H, in order to draw the A to H thing, you will actually intersect from outside or the inside. So that is an advanced go into that way. Okay.
Excuse me, sir.
So this is a complete graph with 4 vertices, which is planar graph. Okay. Now you see no two edges intersect each other in between. So they will all meet at vertex points only. So these kind of graphs are called planar graphs.
Excuse me, sir. Here, F and G is edges crossing D, H and E, H, no, sir. Then it will be planar graph, sir. Planar graph, no cross of edges, no, sir.
This is not planar graph.
Okay.
This is non-planar graph.
Okay, sir.
Okay, don't get into much deep into planar and non-planar stuff. Understand planar graph, you can draw that particular graph. If you able to draw that particular graph in such a way that no two edges intersects in between, like this or like this. There are many intersections in this graph, like this. So if there are 5 intersections we have, so you can bring this E outside, then this and this will be removed. Like this you can minimize the intersections, but ultimately what happens is you will not be able to draw this particular graph on the plane such that each and every edge intersects only at vertex. You cannot draw this. So that those graphs will fall into non-planar thing. So planar means you can able to draw the graph on the paper such that no two edges intersects in between. Okay.
Okay.
Yeah.
Yes, sir.
Let's move and see this minimum vertex cover also. So minimum vertex cover is also one more important field in graph theory, where what we do actually is we have the vertex set, right? So here the vertex set is something like, so maybe the vertex set is A, B, C, D, E, F, G, H, right? So this is the vertex set. So out of this complete, there are 8 vertices. Out of these 8 vertices, we need to find the smallest subset. So from this V, we need to find the smallest subset. Let's name it as V dash, which is a subset of V, such that it covers all the
So you are not audible, sir.
We're not able to hear you.
Yes, sir, we're not able to hear you.
Yes, sir, we are not able to hear you.
I think there might be some network issue from sir's end.
Hello.
Yes, sir. Now you're audible.
Yes,
Now you're audible.
When did I lose the connection?
While you are explaining V
V dash.
V dash.
Oh, okay. So let me get
Sir,
the
screen is not visual.
Yeah, let me get the co-host access. मैं चलते ही रह रहा हूँ, like I kept on explaining. Give me some 2 minutes, okay?
Yes, yes.
Just a second, I will be back in a moment. I will just have a sip of water.
Yes, sir.
Yeah, just 1 more minute, okay?
Yes.
Okay, sir.
Okay, we got the access. Let me share the screen.
Yes, sir.
Okay, so did I start what covers means? Did I?
No, sir. You
No.
just
From V dash. V dash.
Okay, okay.
V dash is a subset of V.
Yeah. So this particular, okay, I got it. Let me re-explain this. So we have the set of vertices with us, the graph vertices. There are 8 vertices. From this particular set, we need to have a subset. You know what is a subset, right? So from a set, we have to select few elements, and what I want is the smallest subset, such that it covers all the edges in the graph. So what this covering means is, so if I have my vertex A in V dash, if I had vertex A in V dash, then this particular edge, so this edge, and this edge is covered. So that is what covering means. Covering means if I pick any edge in this particular graph, any one of the endpoints and vertices should be in my V dash. So if you didn't understand that thing, what you have to do is you have to select few vertices in this particular graph such that if I select this vertex, then this edge is covered. Like this, I have to select some vertices such that every edge is covered. So that is what I have to do. So for that, actually this is for big graphs, this is very impossible to do. So this is not possible. We cannot find the minimum vertex cover. But for smaller graphs like this 8 vertices or 10 vertices, we can actually find. There is a method to find. So what we do is we pick the vertex which has the highest degree. So you know highest degree, right? The more number of edges that are connected to that particular vertex, you pick that vertex and you pick that vertex and keep it in the V dash. Okay. So let's say here we have vertex D with 4 degree 4, vertex B with degree 4, vertex E is also degree 4, vertex H is degree 5. Okay. Let us take vertex H into the V dash. Why I am taking like that? Because I have to take the minimum vertices and cover all the edges. So by taking this vertex H, I actually covered 5 edges at a time. So then it will be easier for us to pick the minimum vertex cover. So if I choose H, so then this edge is covered, this edge is covered, this and this edge is covered. Okay. Now next go to the vertex which has highest number of edges connected to that vertex and also not covered edges. Highest number of not covered edges. Now you see vertex B has 4 uncovered edges and also vertex C has 4 uncovered edges. So you can choose either of it. So let us choose B. So you can choose either of it. So like this you can proceed. So HB. So now what I cover? I covered this and this. Okay. Next I have to cover this edge and this edge. And what else? FG edge. I have to cover FG edge, FD edge, DE, EG, okay, CA, CE, CG. So these many are left. Next I have to choose one more vertex cover. So now you see this FD need to be covered. Anyway this FD need to be covered. So I have to choose any one of the vertex in my V dash. So which one is the best one to choose?
E, I think.
D.
D. Okay, let's choose D.
He will cover more edges.
If I take D, then this is covered and this is covered. So this is anyway covered with H. Okay. Now again I have to cover FG edge. FG. And EG.
Sir, when we take B, D is also covered. So we should take E or C so that others are C, B or C, then others are going to cover.
Okay, if you take E or C, even that is also, see, let us say V dash star. So there is
and
one
I'm
more.
saying because whenever you take B, the D is covered through the B and H, right? So H, B, and C, then C will cover E and G. Those vertices are not covered yet.
No, it's not covering the vertices, it's covering the edges.
Edges. I'm saying, this is covering the edges.
See, if you choose C also, anyway, you should, for this particular edge, you should either choose D or E. There is no other way.
Okay.
Correct? So in our
Sir,
vertex,
you complete it first, sir, so that the others can ask.
Correct.
Otherwise, it will be confusing.
Confusing, correct. Right.
Yes, sir.
So we have taken D and covered this and this. Now we have to cover FG, EG, CG, CA, and CA. So these many are left now. So if I take G, then this is covered, this is covered, this is covered. Now I am left to cover with only two edges, which are CE and CA. So which one should I choose? C. So now see, this particular V dash is a subset. So if I rewrite in the ascending order, it is like B, C, D, H, G. So this particular V dash is a subset of V. And also this is the minimum vertex cover. So these many vertices I have to choose. Definitely I have to choose 5 vertices in order to cover all the edges. Now this is also, once I take C, this is also covered. So I should take this. What this tells is I should at least take 5 vertices in this particular graph so that every edge is being covered. So that means if I pick any edge in the graph, either one of the end vertex will be in V dash. So you can check by taking any edge. So you take B, FD. If you take FD, D is in our vertex cover. FG, G is in our vertex cover. HE, H is in our vertex cover. Like this. CE, BF, B is in our vertex cover. Like this. If you take any edge, at least one endpoint, at least. So you can have both the endpoints. If I take BC edge, B and C both are in my vertex cover. It can also happen, but at least one endpoint end vertex should be in my V dash. So that is what minimum vertex cover means.
Sir, here numbers should matter, right? Because we might have various combination also.
Yeah, various combinations. That is what I said. This is minimum vertex cover. This is one minimum vertex cover.
Yeah.
Okay.
Sir, in this case, we cannot just go blindly and select any vertex, right? Because the number, as you said, the number might change.
Yeah, not every time, but 99% you will get the correct answer if you start with random vertex. But there will be 1% chance of you going like you may selecting 6 vertices.
Yes. So in that case, that
our answer will be wrong. Did I lose connection again? Hello?
Yeah, no, sir. No.
Sir, so in that case, our answer is wrong or what, sir?
Wrong. In that case, answer is wrong. See, when I am getting minimum vertex cover with 5 vertices, then having 6 vertices will not be the minimum vertex cover. That might be a vertex cover, but that will not be a minimum.
Sir, here the order matters or not?
Which order? Order doesn't matter, man.
Because while you have selected D, we can choose C or another else also.
Yeah, you can. Order doesn't matter. In sets, order doesn't matter. Okay. One more surprising thing about this vertex cover is once you have the minimum vertex cover with you, you look at the elements or the vertices which are not taken into the vertex cover. So what are those?
The independent set.
Yeah. What are those vertices? I didn't choose for. Yeah. A.
E.
F.
F.
So if you look at A, E, and F, okay. So this particular A, E, and F are independent set, and it is the maximum independent set we can have. So you can check, verify it. So maximum independent set, I can have only 3 vertices, not more than that. So that is what it is. When I say AEF, that is not the only maximum independent set. There might be another independent sets like BCH, not BCH.
But the number will be 3.
But the number will be 3. So DGA. So DGA is also a minimum vertex cover. Okay. But the number is 3 only.
What do you mean by
Sir, here minimum
what do you
I didn't get it.
Hello, sir.
What do you mean by it?
Yeah, I understand what do you mean by uske baad I'm not able to hear.
Sir, I think he's trying to say maximum independent set definition.
Achha, maximum independent set definition. So maximum independent set is also a subset from the vertex set where all the vertices I choose in my set doesn't have a direct edge. So AE, AF, EF. So we don't have any edges connecting. If I choose any of the two vertices in my set, independent set, they should not have a direct edge connecting. So that is what an independent set is. If I can take the maximum possible number of vertices into my set, then that is called a maximum independent. But yeah, main takeaway in regards of maximum independent set is, once you find the minimum vertex cover, you don't need to separately find for maximum independent set. You take the vertices which are not in the minimum vertex cover, that forms a maximum independent set. So from this, what I can write is V1 union V prime is actually the vertex set. Okay, set of all the vertices in the minimum vertex cover with set of all the vertices in maximum independent set will be equal to the vertex set.
Sir, here minimum vertex cover, if I choose B, E and D, it will cover the whole vertices.
B, E
and D.
B, E and D. Will it cover FG edge?
Yes, sir, because E is connected to G and also H.
So E connecting to G is not the matter. What I said is, every edge covering means either one of the end vertices of one edge need to be in my vertex cover. So that is what covering means. So this particular edge is covered means either F or G must be in my vertex cover.
And sir, here we are dealing with direct connection, not indirect connection, right?
Not the indirect connection, direct edge join. Like
direct join.
Yeah.
Sir, why in V1, as you said, there is no direct connection, so A and E and F you only took. We have also, you have not also direct connection of A to D.
See, that is what I said. So this is one maximum independent set which I have got from this particular minimum vertex cover. So you can have A, D and G also. So this is also a maximum independent set.
Yes, sir.
I'm not talking about this is the only maximum independent set. I am saying is, what I am saying is, this is also a maximum independent set.
Okay.
Okay. Yeah. So main takeaway is this. And this, what is the minimum vertex cover? This is what.
Okay. Well, maximum is not important.
Yeah. So okay, so that is about minimum vertex cover, graph coloring, and let's look at what adjacency matrix is. So as I already said, adjacency matrix is not a new thing. It is actually another representation of graph. And why we must have another representation is because we cannot directly give graph into the machine. So in a computers, graph is actually represented using this adjacency matrix, because these numbers can be stored in the computer, not the graphs. Or the graphs cannot be input, or the computer language cannot understand the graph. So for the computer purpose, we actually write, or we actually represent that particular graph in this particular adjacency matrix. Now this is an adjacency matrix, let's suppose. So how do we get the graph from this adjacency matrix? So each of the row represents one vertex. So let's name the vertices like A, B, C, D, E, F. And also each of the column also corresponds to one vertex, A, B, C, D, E, F. So whatever the order you follow for these rows, the same order must be followed for these columns also. Okay. Now once you have that, so the entries represents whether there is a direct connection or not. So this is what the representation. So whatever the entries, so let's say A is the entry. So A, I, J. So I throw jth column element A, I, J will either take 0 or 1. This will be 0 if vertex I is not, or let's simply say, if I comma J does not belongs to the edge set. So this particular direct edge is not in the edge set. And 1 if Ij is an edge in the graph. So if I is directly connected to j, then our aijth element will be 1. If I is not directly connected to j, then aij will be 0. So simply you look at this particular vertex here. So there are 6 vertices. So let's draw the 6 vertices. Okay, once you draw the 6 vertices, so from row to column, so edges will be from row to column. So this particular 1 represents there is an direct edge from A to C. So this particular 0 represents there is no direct edge from A to A, and this 0 represents there is no direct edge from A to B. This particular 1 represents there is a direct edge from A to C. So from row to column. So there is a direct edge from A to C. So this particular 1 represents that. So 0, 0. So there is no direct edge to D as well as to E. And there is a direct edge from A to F. Okay.
So this is only for, sorry sir, can I ask?
Yeah.
Okay, so this is only for undirected graphs, is it?
This is directed graph. I am drawing the directions.
Ah, right. Sorry.
So I will tell what happens when it is an undirected graph. So how we can identify by looking at the adjacency matrix whether the given graph is undirected or not.
Reflection will be there. 1 0 0 1. Like
correct.
2 3
So
3 2.
we will talk about that. Let us complete this graph first. So we will go row by row. We started from row 1 and look whether vertex A, there are edges from vertex A to some other vertex. So there are 2 such edges from A to C, from A to F. Then we move to B. So there is a direct edge from B to A. So this number 1 indicates from B to A there is a direct edge. So like this. So from B to C, and there is nothing else. So all the zeros. So you look at ones basically. So from C to D there is a direct edge. And from C to E there is a direct edge. From D to E there is a direct edge. And from E, you look at the row E, all the entries are 0. So that means there are no edges that are going from E to any of the other vertices. So from F, there is a direct edge from F to B. So this particular one represents that, and everything is 0. So now you see this particular graph which we got is actually represents this particular adjacency matrix. So the name itself says that adjacency matrix. That means it gives you which vertices are adjacent to each other. Okay. So now
I have a question. This one. I have seen questions where adjacency matrix are given. And when I draw the graph, it becomes very dirty. So is there any way? Means here it is very neat and clean. There was one question in graded assignment 11. I tried to make that graph, but it was very dirty. Means I was not able to do any type of computation on that.
So my suggestion is always take in a circular manner.
I took that circular manner also, and when I saw that solution, it was
very neat.
Something different. Means yeah, sir. It was
I
very
only
neat.
drew that graph.
There was no cross edges.
Yeah, I remember.
Yes, sir. So how can we get that intuition? We have to draw it like
it's
that.
Nothing like that. There will not be any shortcuts to it. So once you draw the graph, so I just remodified it. Like I also drew like you only. But what I did is later I just remodified the graph by looking at how I can draw it neat. Okay, that is
one approach that I take is this. Suppose we are having A to C, then I directly draw a edge from A to C, then A to F. From B, it is F. A, then I create a and I fix it as B to A and B to C. That way also I go. So that's a good way to do it.
If we put the F to the above, it will be more open graph.
Yeah, more clear graph maybe. So yeah, that is what. So once I draw the graph, if you wanted to present it neatly, so you can remodify your graph. That's it. That is the shortcut. I know that is not even a shortcut. Okay, but yeah, again the main the main takeaway is, once I give you an adjacency matrix, were you able to draw the graph or not? Everyone?
Yes, sir. Yes, sir.
Matrix,
Yes, sir.
can you able to draw the graph, whether it is neat or?
Yes, sir.
Yes, sir. We
Yes,
can.
sir, we can.
Yeah, you can, right?
Yes.
When a graph is given, so same vice versa, you can get the adjacency matrix. So if there is a direct edge from A to F, then you should give 1 here. If there is no edge,
Yes, sir.
you give 0. So for that, what the shortcut or the suggestion is, first you fill once. So you fill in the table, you fill once, and later you put zeros to everywhere, every other place. Okay. So this is what adjacency matrix is. And yeah, one more important thing is, if from the adjacency matrix, how do we get to know that whether it is directed or undirected? So look at the adjacency matrix and take the diagonal. Look at the diagonal. So once you look at the diagonal, that will be mirror image. So what if I write it in the mathematical terms? So Aij will be equals to Aji for all I not equals to 0. Okay, what it means is, if this is 1, from B to A is 1, so if it is undirected, from there should be an edge from A to B also. So if there is 1 here, there should be 1 here also. So it will be symmetric along the diagonal. So if your adjacency matrix is symmetric along the diagonal, then that particular adjacency matrix represents an undirected graph. So now tell me whether this is symmetric or not.
Not symmetric.
No, sir.
No, right? There are
Not symmetric.
Not symmetric.
There are ones here, but there are zeros here. It is not symmetric. So you can easily guess that this particular adjacency matrix represents a directed graph.
Okay.
Okay. Yeah. So yeah, that is about.
Sir, one more thing. For this adjacency matrix, we will get always means we can say even number of vertices, right?
Why?
Means even number of vertices means, sir, rows and column will always be the same.
Rows and columns will always. It's like square matrix.
So okay. So is there any means graph theory apart from square matrix?
No.
Oh, okay. Okay.
You tell me, will there be like number of rows? Not.
No, just asking, sir.
No.
Yes. Okay.
Sir, I have a doubt. Sir, in minimum vertex cover and color theory, will it always be undirected graph or it can be directed also?
In this particular course, we deal with only undirected graphs.
Okay.
Okay.
So it can be directed also, but we are not dealing with it.
We are not dealing with it. Yeah.
Okay. Thank you, sir.
Okay. Now let's come to this BFS and DFS. So I hope everyone know what that algorithm is, like what breadth first search means and depth first search means. So I'm not going to deal with that thing again. So I have explained it in week 11 or 10 session. You can go back and watch it. It's an open session. But I just wanted to recall one thing. How do we predict the graph if I give you a BFS tree and DFS tree, or if I give either of it? How do you predict the graph? So there are few steps, few conditions maybe, or few conditions which we have to keep in mind in order to predict the graph. So those are, if I have given you the BFS tree, so let's start with BFS tree. If I have given you the BFS tree, then these three always follows. So what it is, the first point is, the original graph will have all the edges which are in the BFS tree. Okay, this is for sure. So if I draw the BFS tree from an original graph, whatever the edges in the original graph, those edges only I will use for BFS tree. This is for sure, right? This is correct. Is this correct?
Yes, yes.
So
Yes,
the
sir.
original graph
Yes, sir.
will
Yes.
contain all the edges which are in the BFS tree, which you are seeing. So if I have given you the BFS tree, I said, right? So once I given you the BFS tree, there will be some edges, right? So those all edges will be in my original graph. That is for sure. You cannot remove one edge from the BFS tree and predict it as an original graph. So that is for sure. And the next step is for BFS tree, original graph can have edges between a two vertices which are on the same level or one level above or one level below. Okay, I have an example also, but those who understand the levels just recall. So in that lecture we have completely discussed that, right? So just recall what we have discussed. So we have levels. This BFS does algorithms. This BFS algorithm works like it actually searches like level by level, right? So each of the level we know, and in that levels, if I wanted to draw an edge or if I wanted to have an edge between two vertices which are not there, those edges not there in the BFS tree. So only those vertices which are on the same level or one level above or one level below can have edges between them. So this is also for sure. And this is also for sure that in the original graph cannot have edges between the two vertices which have more than one level difference. Okay, these are the three important points we should keep in mind when we are predicting the graph. So let us take an example first and I will come back to DFS next. So this is how the BFS tree will be given to us. Okay, mostly undirected. Okay, so we are not dealing the directedness here. So let us deal with undirected only. So this particular BFS tree is given to us, and once the BFS tree is given, you just write the levels. So this is, you take level 1 or level 0, any of it, but this is one level and this is another level and this is one more level and this is another level. Okay, there are four levels in this particular BFS tree. Now what is the first point says? Original graph will have all the edges which are in the BFS tree. So I have AB edge, AC edge, BD, BE, EG, EH and CF. So these all edges will be there in my original graph. So I cannot remove any of the edge. So along with these edges, there will be few more edges and which makes it as an original graph. And what is the second step? So all these edges are there in my graph. And the second step is original graph can have edges between a two vertices which are on the same level. So you see B and C vertices are on the level 1. So B and C can have an edge between them. So can have, it's not must. So it can have or cannot have, but it can have. Okay, this is for sure. And you see level 2, once you come to level 2. So level 0, we don't have any two vertices, same, we have only vertex here. In level 1, we have B and C vertices and there is no edge. But what the prediction is, it can also have the edge between them. What it says is, even though it has an edge between them, the BFS tree remains the same. So that is what it says. And again, in the third level, we have DE. So sorry, second level, level 2. So level 2, there are three vertices and I can have an edge between them. So DE is a possible edge. EF is also a possible. DE is also possible edge. Okay, I can have edge with same level. So finally, in the last level, I can have an edge between G and H. Now the second point is not only the same level, I can also have edges between one level above and one level below. So what is that means is, so when I consider vertex A, so I can have an edge from A to other vertices which are one level below or one level above. So there is no above level for A, and also the below level already the edges are there in the BFS tree. So nothing to do with vertex A. So let's come to vertex B. So once we come to vertex B, so vertex B is in level 1. So vertex B can have edges with level 0 vertices and level 2 vertices, one level above or one level below. So once I look for level 0, which is above level, so B is already connected to A, and I cannot have, there are no other vertices which are not connected to B. Like that, if I proceed, so B and F, so B is in the level 1 and F is in the level 2. So these two can have an edge directed. In my original graph, this is also can have, it's not must have. So yeah, and again from C, if I see from C to E, I can have an edge. From C to D, I can have an edge like this. So I'm done with level 1. I can go to level 2. So for level 2, we have seen for above level, we have to look for the below level. So FH, DG, DH,
FG.
Yeah, FG. So these are the only possible edges that the original graph can have for this particular BFS tree. Okay, and what all the vector edges are not possible? Not possible means that is the third point we have. So the third point says the original graph cannot have. Actually, we cannot say that must not have. It is cannot have or must not have. So that means definitely I am sure that if the vertices are from more than one level difference, then I am pretty much sure that it cannot have an edge. So from level 0, more than one level is from level 2 to level 2 and level 3. So A to E, A to E. So the red edges are not possible edges, definitely not possible in the original graph. So this is also not possible. This is also not possible.
Sir, I just wanted to one thing pointed out. Sir, you connected the graph of B to F. But sir, normally if we see that BFS follows list option, that is first in, first out. So
Yeah,
if we were going to A, we get B and C. So we solve B first, and we see B has two neighbors, that is D and E. So if F would have been an edge, then F would have come in with that edge also, and then C would have left with maybe C can be connected with D and E and F. But if C is connected with D and E, or C is connected with D and E, so that's why C doesn't connect with D and E, because they are already checked to B. But F was the part which was unexplored, so that's why C was directly connected to F after that.
Okay. So you have gone that way. What if I have searched from A, B, next I went to C?
Okay, if we get to C.
If I went to C, then I will explore F.
Then I will get D and E also.
Okay, I will draw an original.
Okay. Yes, sir. I got that. I got
Okay.
it. It's a different perspective. When I got first to B and then C.
So it can have. You are for one. You are going in one. But maybe there are other ways also.
Yes.
BFS tree is always not unique.
Little louder, please.
Sir, BFS tree is not always unique.
BFS tree is unique, but I can have for different graphs. I can have the same BFS tree.
For same graph, BFS is always unique.
BFS is always unique. If I start.
What about DFS, sir? What about DFS?
DFS is also unique. See, if I restrict you to go in one order.
While drawing a undirected graph, we reaches get an alternate either to choose this way or
Right,
this way.
right. Yeah. So that is what I'm saying. If I said you the order, so if I have given you the order, then it is unique. If I didn't mention any order, then you can
Suppose,
explore.
sir, you have given me a graph and said construct a BFS tree. Source is whatever you have provided. So we can have multiple BFS.
Multiple BFS. Yeah.
So that's it is not always giving unique tree.
Not always unique tree. But the levels will be same.
Yeah, labels are same, but the tree is not unique.
Tree may not be unique. Correct. Correct. Whatever you said is correct. If we mention the order, like you just go with the alphabetical order, or your search should happen in the alphabetical order or the numerical order, then BFS tree and DFS tree are unique. Okay.
So will we get the slides?
Yeah, you will get the slides.
Okay.
And yes, the similar pattern from level 1 to level 3, I cannot have edges. So C and H cannot have, F and G cannot have, C and G cannot have, and B and H cannot have. So ultimately what it says is these edges, so the red colored are not possible edges. So in my options, if I see any graph having these red edges in the inside it, then definitely it will not be an original graph. Okay, and green color one are possible edges. Okay, these are not possible edges, and these are green colored edges are the possible edges, and black colored are the BFS edges, tree edges. So this is how, using those 3 points, this is how we predict the original graph using BFS tree. Understood?
Yes, sir.
We have discussed
Yes,
in
sir.
previous class also, but anyway, I'm just recollecting it. So if I have given you the DFS tree, instead of levels, we have branches here. So here also I have written 3 points. So those 3 points are, the first point is pretty evident. So the original graph will have all the edges which are in the DFS tree. So this is pretty evident. And the second point is, so this is what the difference between BFS and DFS. So the original graph can have edges between two vertices which are on the same branch. So I will explain what a branch is. But if it is from the same branch, how many levels far it is doesn't matter. So there is no levels here. Okay. So in DFS tree there are no levels, but there are branches. So in the same branch, from any vertex to any vertex, if there is no edge in the DFS tree, I can have an edge. And the third point says the opposite of second point, or the implication of the second point. So the original graph cannot have edges between two vertices which are not on the same branch. So if I have two vertices which are from two different branches, then definitely I cannot have an edge between those two in the original graph. So these are the 3 points. We keep these 3 points in the mind. And so the same graph I have taken, the same tree I have taken, but this time I said this is DFS, not the BFS. So what are the possible edges we will draw, and what are the not possible edges also we will draw. Before that, I mentioned the branch. So branch means, so it starts from the root vertex or the starting vertex until the last point is called a branch. So this particular ABD is one branch. And there are 3 other branches. So this is another branch. So ABEG is another branch. So treat it like a tree. So if it is a tree, so these will be like a branches. So this is one branch, this is another branch. This is one more branch. And this is the final branch. So there are 4 branches in this particular DFS tree. Now once you identified the branches, now what we said, recollect the second and third points. So what it says is original graph can have edges between 2 vertices which are on the same branch. So let's consider the first branch. So AB there is an edge, BD there is an edge, but DA there is no edge. From the points we have is DA can have an edge, it doesn't matter, the same DFS tree is followed. So if I draw the DFS tree, I will get the same. So I can have an edge between A and D. Similarly, once you observe, A is actually, this particular vertex A is actually in every branch. Correct?
Yes, sir.
So the starting vertex,
Yes, sir.
that particular vertex A is in every branch. So what it says is from directly you can predict that from A you can have edge to any of the other vertices. So like AE I can have edge, AG I can have edge, AH I can have, AF also I can have an edge. Okay, so these are the possible edges from vertex A. Now let's go to vertex B. So from vertex B, I see ABD is one branch. So I cannot ABD in that branch. B already has all the vertices are connected. Now consider ABEG. So in this also only G is left. So I can have an edge between BG because B and G are in branch 2. Vertex B and G are in red branch. So I can have edge. Similarly, from B to H also possible because B and H are in green branch, the third branch.
Yes.
Yeah. So these are the possible possible edges from B. And from E, if I see from E, nothing.
GH both are possible.
GH are possible, but GH, EG and EH are already the
direct.
Okay. So these are the possible edges in the DFS tree. And what are the not possible edges?
Sir?
Yeah.
DE.
Yeah.
Yeah, DE.
EF.
Asking doubt.
Yeah, I was asking.
And DX, they are not possible.
Yeah, Ogendra, just hold a second. Do you have any doubt in this particular topic?
Yeah, did you say that G and H can be possible?
No, I didn't say G and H is possible. I said EG and EH are possible. But anyway, in the DFS tree, it is already given that EG and EH are the edges.
Okay. Yeah, thank you, sir.
Okay. Now the not possible edges are, you see the vertex B, which is in this branch, 2 branches, and vertex C is in the 4th branch. So definitely vertex B to vertex C cannot have an edge. Similarly, B to F. So B and F are in the different branches. Similarly, DC. Okay. DE. Sorry, C, CG, CH. Okay. DE, DG, DH, and DF.
DF, sir.
And yeah, there are more edges which cannot be drawn. EF.
GH.
Yeah, GH. GF.
HF.
HF. So see, these many not possible edges are there. So if I take 2 vertices which are of different branches, then definitely there cannot be a possible edge between them in the original graph. So only possible edges are these green edges. So there are very limited 1, 2, 3, 4, 5, 6, 7. So in the original graph, I can only have 7 more edges in the original graph, not more than that. Okay.
Sir, there is no formula like in graphs we calculate number of edges n minus 1 by 2 or for tree we calculate n minus 1.
No. I understand, but no, nothing.
Sir, can you repeat the last point you said? N minus 1.
What I said?
It can have only n edges.
I didn't say anything that.
Okay.
Okay, so this is about the BFS and DFS. Let's move on.
Sir, what?
Sir, excuse
Sir,
me,
I
sir.
have.
When we are given 4 multiple options and we need to predict the original graph. So in that case, is it right to start like this and which are possible and which are not possible so that we can check option by option?
Correct. But
yes,
what I recommend is you draw the not possible edges. Better to eliminate the options.
Yes, sir. Yes.
Okay,
From the not possible edges, we can eliminate the option.
You can eliminate the options.
Thank you, sir.
Okay.
Sir.
Sir,
If the vertex are numbers, we go with the smallest one. Sir, but what if the vertex are given as alphabet and it's not starting from A?
What do you mean by that? We will give you the ordering, right? If we didn't give you, you can draw whatever you want.
Okay.
Sir, we should start from top to bottom. Is it, sir?
Top to bottom means?
I mean, choosing the branch like from top.
Yeah, top to bottom. So you go till the degree 1 vertex. So that
Yes,
will
sir,
be a
that's
branch.
what he is rising, sir. Okay. It is given alphabet or something like that.
So, okay, you don't worry about that, okay?
Sir, I have one question here. So, did you explain in open session how to derive BFS to original graph?
Yes.
Means not just age. Means suppose BFS tree is given and we have to find the original graph by not looking into the options.
No. We cannot find the original graph. We can predict the original graph. That's it.
Okay, so means suppose you want to predict the original graph. So we have to find the from option where that not possible graphs are not included, right? Okay, but just by looking into it, no need to write means to follow that algorithm.
No need.
Okay.
Okay.
Means we cannot spend means more than 5 to 7 minutes only on single question. Just by following the algorithms.
Correct. Okay. So look into this. So how
multiple star?
Multiple
star?
Multiple
important.
So if a DFS tree is given to you, or if you derive a DFS tree, it is not given to you, we have given you the graph. Okay, my question is, you start from vertex A and follow alphabetical order. Okay, after following alphabetical order, draw DFS and find number of forward edges, number of backward edges, and number of cross edges. Okay, so this is my question. So I have given you all these things. Okay, and one more important thing is forward edges, backward edges, and cross edges will only be there in a DFS tree. Once you compute the DFS tree, only on the DFS tree, and that too only on the directed DFS graph, not on the undirected. Okay, so this particular forward, backward, cross, so edges having directions only will have a forward and backward. If there is no direction to an edge, if it is an undirected graph, there is no point of calling it as forward edge or backward edge. Okay, understood the point? So this is only for the directed graphs, and in the directed graphs also, after computing DFS tree, by comparing the original graph and the DFS tree, we will classify whether it is forward or backward or cross edge. Okay, so first and foremost thing is you have to compute the DFS tree of this particular graph starting from vertex A. Okay, now tell me. So I am starting from vertex A. In the alphabetical
Then
order,
we'll go to
A to B.
B.
then
A
we'll
to B.
F.
F.
B to C.
A
B to C.
H.
C.
A to B, B
alphabetical order, so you have to go to C.
Yeah, C.
Then we'll go to E.
E. Then we will come back. And
Come
Then
back to C
that's
and then
no,
go
they've
to
come
G.
back C. From C, we'll go to G.
From E, we will come back to C, correct?
C to G.
We'll go to
Then
G.
we'll come G.
C to
And
G.
from
Then
G
H.
to, we'll go to H.
H.
Yes, correct.
F or
F.
Yes,
F,
sir.
sir.
F should come.
H. Then again, we will come back to G.
G to F.
Then G.
G to F.
F to D.
Again back to G.
F
No,
to
F
D.
to
No,
D.
F to D.
I'm not able to see.
Let us make it shorter.
Yes.
Let me zoom a bit.
Previous one is, this one is better.
Okay, this is good.
And
Yes,
then
sir.
we will go back to F and then go to
F to H.
From we go back to
F.
F.
H.
Yeah.
From F to then H.
H.
From F to H.
Correct.
All done, sir.
So
Yes.
3, 4, 5, 6, 7, 8. All done. Correct. So once you have drawn the DFS, just make sure whether you have all the vertices in the graph, or at least you should cover all the vertices. At least you are covering all the vertices. So wherever it is reachable, you should cover. So actually what it tells is this particular, from if you start from vertex A, you can actually go to every other vertex. So DFS tree is
Sir, can't we go from A to B, B
Hello?
to F also?
A to B, B to?
You are not audible, sir.
F.
Am I not audible?
Audible, sir. Audible.
Yes, sir, you are
Yes,
audible.
sir, you are audible.
So I said that we have to follow the alphabetical order. Okay. From B, I can actually go to F, D and C. But in alphabetical order, C comes first.
Sir, it was not said that no in alphabetical order, then we can go.
Then you can go. So that is what, then you can go.
And we can have multiple DFS.
Multiple DFS, correct. But as I mentioned that you follow alphabetical order. So this is the possible DFS starting from vertex here. So now once we have the edges, now these forward edges, backward edges and cross edges are the edges which are not in the DFS tree, but which are in the original graph. Okay, just mark the edges which are in the DFS tree first. So AB is in
both the
AB is a DFS edge.
yes.
So these are DFS tree edges. So BC is a tree edge and CE is a tree edge. CG, like this. Mark all the 7 edges. So when you have 8 vertices in your tree, you are going to have 7 edges. So C to G, G to F, F to H.
F to D.
Sorry.
Yes, it's right. F to G. S is right, sir.
F to D, right? F to D
F to
and F
H
to
is
D.
also there.
Yeah, correct. So F to H is also there. What are not there? Like AC is not there. AH is not there.
BF, BF, DE,
BF,
BD is not there.
DE,
HD.
G. There are many edges which are not there in the DFS tree. So now what you have to do is you just try to draw those edges in this particular DFS tree. So I will try to draw the edges. So from A, are there any edges which are not in the DFS tree? Yes, they are. So from A to C and A to H.
Yes, sir.
Correct?
Yes, sir.
So I draw those edges. A to C,
A to H,
A to H. Correct. From A to B, from A I move to B. So from B there are 2 edges which are not present in DFS tree. So I will try to draw those edges. So from B to D and B to F. So B to F and B to D. Okay. So B is also covered. Now let's go to C. So once I am there in C, there are no other edges. So this is done. So this edge is done, then done. And D to E there is an edge. So you add all those
So
edges.
B to E also possible edge.
Why B to E?
B to
In the original graph, B to E is not even an edge. There is no edge. B.
Oh, okay, it's not even okay. The given thing is we have to say on the. Okay.
So D to E there is an edge.
Sir, we cannot, in question if they ask whether B to E is a forward edge, so it's wrong,
Then
right?
D to E not possible. This is cross
B
edge,
to E.
cross branch edge.
We will talk about that.
Okay.
There is a from H to E.
Now from H to D and H to E.
Yes, sir.
G to H are
G to H. Sir, one thing, sir.
So just wanted to.
Sir, you are drawing the edges from the graph only, or
from the original graph only. This is the original graph given to us, and I have drawn the DFS.
In DFS tree, you are mentioning the from the graph only.
DFS tree we have computed using this original graph. We have computed this DFS tree starting from vertex A and following the alphabetical order. We got this DFS tree. After getting the DFS tree, I am just adding the edges which are not in the DFS tree but which are in the original graph.
Oh, that's right.
Sir, as I said, which is not in the original graph, but just right previous in the previous slide, you told us that we can't change from branch to branch. A, B, C, E is a different branch, and A, B, C, G, F, D is
that is for undirected graph.
Oh.
Okay. These things predicting graphs is okay. See, this is for this predicting graphs for only undirected graphs.
Okay. Okay.
Okay.
Okay. This is for only undirected graphs. So that is why I said this forward, backward, and cross edges in a DFS tree is for directed graphs. So these terms will come forward, backward, and cross only for directed graphs. Okay, this is for directed graphs.
Sir, I have just a small doubt. Forget this. As per alphabetical order, we go to A to B, B to C. Then after that, we can go to D. Just
from C now you are at C. So from C, we have to look at the neighbors.
Okay.
So the neighbors are only E and G.
Okay, got it.
So in that you should take the alphabetical order. So E and G, E is the first alphabet. So E comes before G.
Okay, got it.
Yeah. Let's complete this. D to H is an edge. And H to E is an edge. And G to H. Okay. So now we have added all the edges in the original graph. G to E. Correct. G to E is there. Okay. So these are the edges which are not present in the DFS tree. Now, what is, so we classify these.
Sir, B and D are in the same branch. Sir.
Okay, B and D are in the same branch. Correct. So now you identify the branches of this DFS tree. So this is one branch. A, B, C, E is one branch. And there is one more branch. A, B, C, G, F, D. So this is another branch. And there is a third branch, which is A, B, C, G, F, H. Okay. So there are three branches. Now, what is a forward edge? Forward edge means if two vertices which are from the same branch and having the edge in the same direction as the branch direction. For example, the branch direction is like this. So the branch direction is from A to E. So this is the branch direction. So within this branch A, B, C, I have another edge from the original graph which is from A to C. So even this edge is also in the same direction as, can I have, okay. Kaushal, can you be on mute? I'm getting an okay. So if the original edge, the red edge, so which we draw from the original graph, which are not present in the DFS tree, which is not present in the DFS tree, if that particular edge has the same direction as the branch direction within the same branch, that particular edge, those particular edges are called forward edges. Okay, so AC is a forward edge. So this is a forward edge. Similarly, there are few more forward edges. If you see, if you observe, see, A to H is also a forward edge because A and H are in the same branch, and also AH edge follows the same direction as the branch direction. So the branch direction and the AH edge direction is on the same side. So therefore, AH is also a forward edge. Okay. Similarly, BF, BD. Am I audible?
Yes, sir.
Yeah.
Yes, sir. Audible, sir.
So
Sir,
BF.
but why you have written AC? Why not AE?
Because AE in the original graph itself, AE doesn't have an edge. We no need to talk about that edge. So these edges are from the original graph. If we know this original graph, this is given. Okay, this is given. So you know the original graph, and also you can derive the DFS tree. So once you derive the DFS tree, then you can find the forward edges, backward edges, and the cross edges by following this method. So you draw the edges which are not in the DFS tree but present in the original graph like this, and then you classify them as like this. So from the same branch, two vertices having an edge, and also the direction of the edge follows the same direction as branch follows, those are called forward edges. And the backward edges means the opposite of forward edge. So that means within the same branch, the direction of that particular edge should be opposite to the branch direction. So are there any edges?
No, sir.
No, sir.
No edge.
No, sir.
Right? Within the same branch, opposite to the branch direction, do I have any edges? I don't have any edges. So you can observe.
What about GH in the forward edge?
See, GH is a GH is also a forward edge.
Yes.
Correct. So GH is also a forward edge. And BD, BF, GH is also forward edge. Correct. And backward edges, there are no backward edges. And yeah, cross edges are very easy to observe. So cross edges mean,
Isn't that also A comma B for forward edge?
A comma
B.
Yeah, see, that is what I am telling. See, these black edges are actually the DFS tree edges. They are not classified as forward or backward or cross edges. The only classification happens for those edges which are not present in DFS tree but present in the original graph. So that means these red edges which I drew. So those only we will classify as forward or backward or cross. So cross edges means vertices from different branches. Okay, so if there is an edge between two vertices which are from two different branches, then that particular edge is called a cross edge. So what are the
like GH here?
Yeah.
No, they are from same branches. Sorry.
Yeah.
EG,
DE,
HE, EF, ED,
HE,
EH,
and
HD.
HD. Correct. So these are the cross edges. So the number of cross edges are
Or there is no meaning of downstream or upstream.
No, that is what I said. In cross edges, you don't need to worry about direction of the edge. So if the edge is in between two different branches, vertices, then that is called a cross edge. Okay.
Sir, actually I missed that backward edges thing. Sir, why you have written no?
No means there are no backward edges here. Backward edge means same as the forward edge, like we look in the same branch, but the direction should be opposite to the branch direction. So for forward edge, the direction.
Sir, can you take one example and explain, sir?
So for suppose if in the original graph there is an edge from H to A. Okay. So
Yes, sir.
branch direction is from A to C to G to F to H. So this is the direction of branch. But opposite to that branch direction, there is an edge from H to A.
Okay.
So these kind of edges are called backward edges. And you can identify easily the DAG. You can connect actually DAGs and the backward edges here. So why I am getting backward edges no or number of backward edges as 0? Can I infer something from this graph?
Because there are no cycles.
There is no bidirectional edges between any two vertices.
There is no bidirectional is not correct, but whatever the other people said is correct.
Said
So
it is cycle. It creates cycle.
So backward edges will create a cycle. So let's suppose I just took an example, right? If there is an edge from H to A, now A to B, B to C, C to G, G to F, F to H, and H to A will create a cycle. So if there is at least one backward edge, then there is a cycle in the graph. So can we conclude something more like this graph does not contain cycles, and also this is directed.
DAG.
Yeah. So this
is called DAG.
Directed acyclic graph, which is a DAG. Correct.
Sir, can you do one thing, please? So this is done. So on original graph, can you means make change in graph so that we will get to know what is backward edge? Means you have done the change in DFS tree, right? Suppose there is a path from H to A. So how it will be written?
So the graph will be reversed, right? So that particular edge will be reversed. Okay. If this will be like this. Okay. If there is an edge from H to A, this is how the graph looks like. Then you can identify a cycle here. A to B, B to C,
sorry,
C to G, G to H, and H to E. So this will form a cycle, and therefore it will not be a DAG.
Sir, in that case, you will not write A to H as a forward edge. You will remove this, right?
We will write A to H in here. So this A to H comes here. So the number of backward edges will be 1, which is AH edge.
But in DFS diagram, that A to H representation will be removed, right? As a forward edge.
As a forward edge, we will remove. Like this, it will be removed.
Yes.
It will be like this.
Okay.
Yeah. Sir. सर अगर ग्राफ में बैकवर्ड एज नहीं हुआ तो वो डैग कहलाएगा.
वो DAG. So if there is no backward edge in the graph in the DFS tree, then that says that the original graph does not contain cycles. And if the original graph does not contain cycles and it is a directed graph, then it is a DAG. So which is the next topic we have. So DAGs are basically the directed acyclic graphs. So the name itself tells us the complete picture of it. So DAGs are basically which are directed and also directed graphs which does not have cycles. Okay, so this is a DAG. So let us take this DAG and compute the topological sequence. And also the longest path at the same time. Oh, sorry.
Sir, with this graph, can you please draw the BFS? Not now, but after completion of the session.
So I suggest you try that, na?
Yes, I have tried, but with BFS, I actually fumble sometimes. That's why.
Okay, so let us try to draw the okay. So let us try to draw. Let us try to compute the topological sequence and the longest path too at the same time. So for that, we have to assign two values for each and every vertex, correct? So you tell me how to do it. So I have already explained this topological sequence and longest path too. So topological
start with the vertex which has in degree 0, sir.
Correct.
Because we have to assign in degree values and assign 0 for longest
0
path.
for all vertices.
Topological sequence or topological ordering or topological sorting, everything means the same. Okay, and what we are going to do now is whatever you said is correct. We are going to find two different values for every vertex in this particular graph, which is one is in degree of the vertex and the other is the longest path 2 as 0. So we initialize it as 0. So we will do that. So the red number, remember the red number represents the longest path 2 and the blue number represents the in degree of the vertex. What is the in degree of vertex here?
0.
0.
P
2.
G
0. 1.
0.
1. 1.
Did everyone need break or what?
Oh, no, sir.
No, sir. I think we need to go long. Algorithm part is left.
I know. Algorithm part is left. I know.
Yeah.
At the end, if time permits, can you please again go back to the minimum vertex cover?
Whatever I discussed is sufficient. Don't worry about that.
No, actually, I have some question over there still.
Okay.
Sir, if this much big graphs are there,
Firstly, complete all of
can
that.
we complete within time, sir?
This much big graph will not be there. This is for understanding purpose only. If I want to remove, I can remove.
No, sir. No, sir. It's not like that. But is the time will be sufficient or
time
not?
will be sufficient. Don't worry.
Okay, sir.
See, also you have the weightage with you, right? You can expect some 5 to 6 questions from graph theory, complete graph theory.
Yes, sir.
Yes, sir.
And also, sir, please
not more than that.
tell us. Excuse me, sir.
Yeah.
Sir, and also at last, if we have time, please tell us how to identify there is a noise.
There was a noise. Can everyone
please mute?
Yeah.
Please mute.
I will make everyone mute and yeah.
Excuse me, can I ask one question, sir? At last, if you have time, can you please tell us how to identify, how to find the minimum vertex cover? I know the concept, sir, but from the questions, I'm just confusing with whether it is related to vertex cover or coloring. That's what give us confusion, sir.
Okay, we will see.
Okay, sir.
Please
Thank you, sir.
complete first. After that, we will take out.
So let us complete this important topics, no?
Okay, sir.
Okay.
Thank you.
Yeah. So what is the degree of vertex edge? I will just write it. Just correct me if I'm going wrong. Okay.
3. 2.
3.
1.
3.
3.
1.
1 and
4.
4.
Okay. Yeah.
Sir, here 0 representing out degree or
longest
out degree?
path.
Longest path.
Achha, longest path.
Yeah,
Okay.
Blue number is for
Topological.
In degree.
In degree. Okay.
Degree of vertex.
0.
Red
longest path
is for longest. So I will write it short. So LPT of I. Okay. So red number indicates this. So what we do is we start with the vertex which has in degree 0. Correct. So identify the vertex which has in degree 0. So the vertex A has in degree 0.
Yes.
Once you identify vertex A has in degree 0, what we do is, so topological sorting, we bring that vertex A to the topological sorting or the sequence, and then what we do?
Remove all vertices.
Then what?
One B will be 0 and C will.
Sir, can you lead us?
Can I?
Let me explain.
Sir,
I'm explaining that only. So we have explained this very clearly in previous sessions, but
yes, sir.
Explain it. Okay. So the topological sequence, for the topological sequence, you start with the in degree vertex A, because the in degree of this vertex A is 0. That is why we start with vertex A, and we take that vertex A to our topological sequence, and later what we do is we remove this vertex as well as the edges that are incident to this vertex.
Sir, please remove in the next figure.
In the next figure?
Yes, sir. Yes, sir.
Then it will be a lot of figures.
No, sir, it will take some time.
It will take a lot of time.
Yes, lot of time it will take. See, if you want a detailed explanation, we have done this in week 11.
No, sir. I don't want to. Next figure. One picture is original, and after the second, we will remove.
Okay. So let us do it here then. Okay.
Yes, sir.
So we have to remove vertex A and the edges that are incident to vertex A. And what I have to do is I have to update. So this is what the updation for blue number
in degree.
For blue number,
reduce.
Yeah, it will reduce by 1. So you will update
in degrees.
Number. And also what you have to do is you have to update red number for edges and vertices. So even the updation for blue number is also for edges and vertices only. Edges and vertices. So for which edges and vertices? The removed vertex. So
for removed one.
Yeah, for A we removed A. So for that A, B, C and H are the edges and vertices. So we are going to update the blue number. So you update the in degrees.
0.
What is the in degree of B? 0.
0.
In
1.
degree of C will be 1. So it will reduce. So this will be 2. So from 3 it goes to 2. So later we update the red numbers for the edges and vertices also by. So the longest path to particular I is actually, you can update it as max of between two numbers. What are those numbers? LP, longest path to I. So we had value,
1 plus
longest path to
LPTI.
The removed vertex U. So let's say removed vertex is U. Okay, if the removed vertex is u, then the longest path to I will be updated as max of longest path to I previously, comma 1 plus longest path to u for all I adjacent to u. Okay, so that means, so you see here for vertex B, the longest path to B, so LPB is actually max of LPTB or 1 plus LPTA. Okay, this is what we do. So max of LPTB is actually 0,
Zero.
0, comma 1 plus
Zero.
LPT of A is also 0.
Zero.
So this is max of 0, comma
0
1.
and 1. 1. 1.
Yeah. So this
Sir,
will be
excuse me, sir. Sir, LPT in the sense, sir.
longest
Longest
path.
path.
Longest path to. So you have longest path to this particular vertex side.
For example, if you take B, what is longest path? How it will be 0, sir?
So we initialize it to 0, right?
Okay.
So initially
All
we have
vertices
given for all the vertices we have given 0. So that is the initialization we have done.
Okay.
Okay. So later we are updating it slowly. So here we got longest path to B as 1 after removing vertex A. So this particular 0 I will remove and I will keep it as 1. I will replace it with 1. Similarly,
I don't understand how it becomes 1, sir, please. Don't mind.
So it's like
you will take max of 0 and 1.
Max
you will
of
get 1.
Yeah, max of longest path to B, comma 1 plus longest path to A. So between these two numbers, I will take the maximum of it.
Okay.
So longest path to B initially is 0, and 1 plus longest path to A is also 0. Okay. Longest path is also 0 for A. So 0 comma 1 plus 0, max of 0 comma 1 will be 1. So from 0 I will update to 1. Similarly, not only if I replace it with C, it will be like max of LPTC comma 1 plus LPTA. So that will also be like max of 0 comma 1. This will also get updated to 1.
1.
And even this will also get updated to 1. Okay.
Yes, sir. Thank you.
Now it is done. Now later what we have to do is we have to do this repeatedly. So what we did, we have to identify the vertex which
In
has
degree 0.
So the in degree
B.
0, blue number 0 is for B.
B.
So what I have to do is I have to add this B to the topological sequence.
Remove all edges from B.
And the longest path to B as of now is 1.
1.
I will add that longest path to B as 1. I will update as 1. And I will remove B and edges that are incident to B.
So why is H 1? Why is the LPT of H is 1?
Same as how we got B.
Okay. So
it was connected to A, right?
It was connected to A.
It was connected to A.
Okay. Thank you.
So you have to update it to 1. Okay. Yeah. So once I remove the B and the edges, incident edges of B, I have to update the blue number and also the red numbers. So once I update the blue numbers,
1, 2, 3.
This will be 4 only.
4. 0.
This will be 0. This will be 2. And this will be 1. Okay. Blue numbers are updated. Now I have to update the red numbers. So the red numbers are already the value. So you see max of already the value, or I have to say max of 0 or 1 plus LPT of B now. I have removed vertex is B. So what is LPT of B?
1.
So you see
0,
0 comma 1 plus 1, which is 2.
2.
So this is actually max of 0 comma 2, which is 2. So now this particular red number from 0, it will update to 2 directly. It won't come to 1. This is 2. Similarly,
Same
I
for
have to,
D.
same for D. So for D,
1.
0 comma max of
2. 1 plus 1.
So it will be max of 2, 0 comma 2, which will be 2. So for D also it will be 2. Same for C. So it is like max of 1 comma
1 comma 2.
1 plus 1. So which is 2.
2.
Okay. Now we have updated the longest path 2s also for the adjacent vertices of B. Now what we have to do, we have to repeat this cycle again.
C.
So C will be the vertex which has index 0. So we will add that vertex C to the topological sequence and number the C with 2. Longest path to C is 2. And we will come back to the graph and we will remove C. Now I have to update only 2 vertices numbers. So this will become 3 and this will become 0. And this particular red number now it will be like
2.
Max of
3.
0 comma
1
plus 2. 1 plus 2.
Yeah, LPT of C. So LPT of C is 2.
2
plus 2 is 3. So max of 0 comma 3 is 3. So this will directly from 0, it will directly update to 3. Similarly, when I come to G, this will also be like max of 0 comma 1 plus LPT of C, which is 2. And again it is like max of 0 comma 3. Again it will go to 3.
Sir, I have a doubt. If two max are same, so we update both of them or anyone?
If two
max were same.
Max were same, what will be max of 1 comma 1?
1.
1 only. So is there any specific of one writing, first one writing like this and second one writing somewhat like this? Nothing, right? Both the ones are same. Max of 1 comma 1 is 1. So you update or not update, the same value will remain.
Okay, thank you.
Yeah, but initially you have 3 and something you got like 1 plus 1. So what will be the max of
3?
3 only. It will not update. That's it. So initially it is 3. Also after this, removing that particular vertex, it is 3. 3 only. Okay. So you have to take the maximum of it. So if both are equal, then maximum is equal to that particular equal number. Okay. Yeah. So similar, if we follow the same approach, now G is the vertex I need to remove because the integrity of G is 0. So we'll do a little quick. So Z 3 should be added there. Okay. Now I will remove G as well as the edges.
You have to go by alphabetical order, right?
Huh?
You have to go by alphabetical order. Why not D then why G?
No, alphabetical order we don't use for this topological sequence. So here we are trying to find the vertex which has integrity 0.
Okay.
If there is a clash between two vertices, then we will give you like you should, at that point you should choose the alphabetical order. Like let's say D and G has at the same time got integrity 0. So which one you should, then you have a choice to choose. Now we don't have a choice to choose.
Okay, sir.
Yeah, once I remove, I have to update the integers. I will update the blue numbers first. This is 2 and this is 1 and this becomes 0. And now the red numbers will be updated like this. So it is max of 3 comma 1 plus LPT of G. So what is LPT of G? It is 3. So 3 comma 1 plus 3. It will be 4. So this will be 4. Even this is like max of 2 comma 1 plus 3. Again this will also be 4. This will also be 4. So this is also like max of 1 comma 1 plus 3. This is also 4. Now the next vertex I have to look for is the integrity 0 vertex. So vertex F has integrity 0. So I will add that vertex F and
4.
It is 4. I remove. And this will be like, this is 0, this is 1, this will update to 5, this will update to 5. So if you take the max of it, you will get 5. So next I have to remove vertex H. So H, and it is 5. I have to remove vertex H and the corresponding edges. And now this will be like, this is 1, and this will update to 6. And this is 0, and this will update to 6. Okay, and I have to remove D, because vertex D has in degree 0. And the longest path to vertex D is 6. And finally, we will remove E, and the longest path to vertex E will be 7. So once you remove this will be like 0, and this will be like max of 6 comma 1 plus 6. So it will be 7. 7. And finally, what we do is we remove this E, final vertex E, and we will add it to the topological sequence. So this is the topological sequence, and this is the longest path. So then the longest path, you see the maximum number as 7. So that means in this particular graph, I have a path from one vertex to another vertex, which has the longest in terms of edges, we say, basically. So there are 7 edges in that particular path, and that is the longest path in the graph. So any other paths are shorter than this longest path. So if you wanted to see, you can start from E. So you just go back. So from E to D, D to H, F to, so if you want to find that longest path, so E to D, D to H, H to F. So just trace back, F to G, G to C. Okay, now you see A to B, B to C, C to G, G to F, F to H, H to D, D to E is the longest path in this particular graph. So any other paths you take from any two vertices, between any two vertices, that particular path will be shorter than this particular path. This is the longest path in the graph. So that is what we find.
Sir, in this we have to follow the topological sequence or the longest path number, because there can be a chance that we can have
more or less you might get, you have to follow the topological sequence as well as the longest path numbers also. So for suppose if you have 2 3s here, if you have this also has 3, okay, this also has 3, that means maybe FG, this particular, okay, that will ruin it. If there is 3 3, or oh sorry, there will not be 3 3. Okay, 3 3 like this. Let's say there is one more vertex like this. So once you trace back, while you are tracing back, once you reach 4, from 4 you have to go to 3 number. So either you can go to G or H depending upon the graph you see. From F, where you can go back. So that particular vertex you should choose. Among those two vertices, which one is connected to F? So by taking that vertex, you have to go back.
Okay, sir.
Okay. Yeah. And yeah, again the same statement. Don't worry about that much. Okay, this is about longest path 2 and.
Sir, this one, if our TS is correct, and without following the longest path algorithm, If we just assign that 0 to the sequence, whether that could be wrong?
Maybe that will be wrong. See,
okay.
Now that this graph has the longest path as length 7, you got it like this. So there may be some graphs where the longest path is actually only 4. Maybe you can get that. So that is within 4 edges I traverse, I can move to from one vertex to any other vertex. So that can also be a possible case. So maybe the longest path may be like this: 0, 1, 1, 2, 2, 3, 4, 5, 5, 6, or very less, or it is like 3, 3, 4, like this. It can happen like this also. So the longest path from A to E is of length 4 only. We cannot say. It can happen. So for this example, it was 7. We got 7. Not always.
So sir, we can say that. It is a count of edges, right? Means path we are following. So suppose from A to B 1, then B to C 2, 1 plus 1 2, C to G, like this.
Correct. In terms of edges,
7.
we are computing this longest paths. Okay.
Okay, sir.
Okay. So that is about the longest path and topological sorting. If you want in detailed explanation, I actually gave you in detailed explanation only. If you still have doubts, you can go back to the session which I have taken in the week 11. So that's an activity session. So there I have explained it clearly how that works. Okay. Yeah. In algorithm part, what I wanted to more emphasize on is, so you should basically know when to use which algorithm. Okay. So let us see first. So the problem statement is like this. I have to find the shortest path from a fixed source vertex to every other vertex in a graph that has no negative edge weights. So I hope everyone know what are edge weights and negative edge weights and positive edge
Yes,
weights.
sir.
Yes.
Yes, sir.
So if there are no negative edge weights, that means every edge has a positive weight, non-negative weight. So in that particular case, if I wanted to find the shortest path from a fixed source vertex to every other vertex, then I can use Dijkstra algorithm or Bellman-Ford algorithm. So I can use both of the algorithms. Okay. If I have negative edge weights, so the same problem statement, but now I have the negative edge weights, but no negative cycles. Okay. So once I have negative edge weights, I cannot use Dijkstra algorithm. I can only use Bellman-Ford algorithm in order to find the shortest path from a fixed source vertex to every other vertex in the graph. Okay. Then later there is one more algorithm which is called Floyd-Warshall algorithm. There is in between one more algorithm which is Warshall algorithm. So that is for only positive edge weights. So to find the shortest path, we don't want that actually. So no need to worry. It's actually for finding the shortest path from any vertex to any other vertex in the graph which has non-negative edge weights. Okay, we didn't deal with it much, so no need to worry about that. But the third algorithm, which is kind of important algorithm, is Floyd-Warshall algorithm. When we use this Floyd-Warshall is, just a second. So to find the shortest path from any vertex to any other vertex in a graph that may or may not have. So even though it has negative edge weights or even though it doesn't have negative edge weights, but no negative cycles. Negative cycles are not at all allowed. So what is a negative cycle? Hello.
Yes, sir.
Sir, can you explain negative edge weight? Just
yeah.
Cycle returns negative values.
A cycle having negative.
Okay, before that, negative edge weight means for a particular edge. So if I have an edge, for this particular edge, if I assign a value like negative weight. So positive weight like 8 or 9, it is like positive weight of an edge. So this particular number assigned to this edge is called the weight of an edge. if that particular weight is negative value, then this particular edge is called negative edge weight. So negative edge.
तो सर हम लोग इसमें बेलमैन फोर्ड यूज करते हैं. बेलमैन फोर्ड यूज कर सकते हैं.
हाँ, बेलमैन फोर्ड we will use if my problem statement says that I have to find the shortest path from a fixed source vertex to every other vertex in the graph.
Okay.
If the problem statement is like to find the shortest path from any vertex to any other vertex, then I have to use Floyd-Warshall algorithm. Okay, this is what negative edge weight is. And negative cycle means if I have a cycle such that, so the weight of the cycle, so what will be the weight of the cycle?
Overall negative.
Yeah, A. So let's say A, B, C are the weights. Weight of the cycle is actually A plus B plus C. So the total sum of edge weights is what the weight of the cycle. So if this particular weight of the cycle is less than 0,
Yes, then it is negative
then
cycle.
this cycle is called a negative cycle. So for example, so if I have like this, and if I have a cycle like this and minus 7, 6, sorry, minus 7, 6, minus 7, 3, 2. So if I compute the weight of this cycle, so weight of the cycle is minus 7 plus 3 plus 2. So which is minus 2. So minus 2 is less than 0. So this particular ABC cycle is a negative cycle. So these particular cycles are not allowed. Or if there are cycles like this, then I cannot perform these algorithms. So no algorithm can be performed if I have a negative cycle with me. So first and foremost thing is I should have negative cycles. Okay. Sorry, I shouldn't have negative cycles.
Yeah, should not have.
Yeah. So I shouldn't have negative cycles. Then depending upon the negative edge weights and only the positive edge weights and the problem statement, looking at the problem statement, I will use whichever algorithm I have to use. And one important thing is, why not use Floyd-Warshall algorithm for every problem statement?
It's time
Because if it is
Any vertex to another other vertex, not from a fixed vertex.
Even it gives for if it is giving for any vertex to any other vertex,
will
so
be
it will
for
give for one fixed vertex, right? If you take
Yes, sir.
it will give.
yes, sir.
Why
So
not?
it is lengthy. It is quite lengthy.
Computation time complexity of Floyd-Warshall algorithm is far greater than Dijkstra algorithm. So Dijkstra algorithm is an easier algorithm, and also
Yes, the easier algorithm to do.
And also with regards to the time complexity, Dijkstra algorithms will give us faster output than the Floyd-Warshall algorithm.
Sir, I have one question regarding that Floyd-Warshall algorithm.
Yeah, we will. I will take it. Let me complete my last particular topic I have, which is trees, minimum cost spanning trees.
So, sir, it would be better if you calculate one Floyd-Warshall algorithm.
Okay, I will take it. I will take it. If you want, I will take it.
Yes, sir.
There is nothing in that. But let me complete this thing.
Say, so you complete, sir, but tell that process we need to remember, or just the conditions which you told is more important.
See, whatever I discuss is more important.
Means like how to solve is not important, but knowing the
Please take
conditions
one example.
is important, no, sir.
I will take an example. Definitely, if everyone agree asking to take an example, I will take and solve the example.
Yes, sir.
Okay? But
Yes, sir, but for small tree.
Yeah.
But that tree should be like this only, sir. This ABCD like this.
Yes, sir.
Otherwise, for computation time, because we have at 8 stats mock
Correct.
test.
I understand. I know. I will take an example, but let me complete this tree.
Yes, sir, sure.
Trees and minimum cost spanning trees. And I know this is an easy thing to understand. But let me recollect your memory and we will try to refresh. Okay. So trees are basically minimally connected acyclic graphs. So there are 3 terms inside this tree. Minimally connected acyclic. So acyclic, we know that there shouldn't be any cycles. So no cycles means acyclic. So what is connected means?
All vertex are connected with each other.
Like between any
two vertices,
there
should be an edge.
We should have path. No need of edge. We should have a path. See, from A to D, there is no edge, but A to D, I can reach from A to D. So if I choose any two vertices, there is a path from that vertex to other vertex is what connected with.
Okay. Yeah.
Okay. So simply your graph shouldn't break at any point. Okay. It should be throughout connected. And minimally means
at least connected to one. At least connected to one path.
Not connected.
If we add an edge, it makes a cycle.
So minimally means this is the minimum I can have a acyclic connected graph. If I add one more edge to this particular graph, this will no longer be a connected acyclic. This will be a connected cyclic graph.
Cyclic.
That is what minimally means. So you can see an example also. So if I wanted to add one more edge to this particular vertex, particular graph, maybe BC. So ABC will create a cycle, or DC.
Yes, then it will create a cycle if you use one edge.
Yeah, if you take one more edge to this tree, this will no longer be an acyclic. This will be a cyclic. So that is what tree means. So these are some examples here. So these are trees. So this is a tree with 4 vertices and 3 edges, and this is a tree with 6 vertices and 5 edges. And yeah, so even if I remove one more edge from this, what will happen? So adding one more edge will create cycle. If I remove one edge, what will happen?
Isolated vertices.
So it will not be connected.
Not a tree.
It will no longer be a connected graph.
Connected.
So if I remove BC, so this will no longer be connected. From A to C, I don't have a path. Or from B to C, I don't have a path. From F to C, I don't have a path. Okay.
But this separate are tree, minimal collect. We can say they are trees, right? ABF and C.
Yeah. These are separately trees, and these are separately connected graphs. But if I look this as a whole graph, then this is not a connected.
Disconnected.
Yeah, this is a disconnected.
Kind of forest, multiple trees.
Yeah, forest. Yeah, multiple trees. Okay. Okay, so this is tree, and there are a few properties of tree which are very much interesting to observe. So first and foremost thing is number of edges will always be 1 less than the number of vertices. Okay. So in a particular tree, if I say there are n vertices, then definitely the number of edges in that particular tree are n minus 1. So only 1 less than the number of vertices will be the number of edges. And also one more important property is there will always be 2 vertices, not only 1. So I just written 1. There will be 2 vertices which has degree 1 in a tree. Those starting vertex or the ending vertex, both the vertex will have degree 1. So in the above examples also you can see this has degree 1, and this has degree 1, degree 1. So there will be there is always be, I have written, there is at least, sorry, there is at least 2 vertices which has degree 1 in a tree. Okay, and this is not that important, but the main important thing is this thing. The takeaway is this. So the sum of all the degrees of vertices of a tree, if I wanted to look at the sum of all the degrees of vertices of a tree, this will be 2 times of number of vertices in the tree minus 2. Is this true?
So can you please repeat this last?
Okay. How many of you know this handshaking lemma?
No, sir.
Like, what is the connection between?
No idea.
What is the connection between sum of all degrees in a graph with number of edges?
2m. Means number of
sum of all degrees of vertices will be
equal to
twice
2 times number of edges.
Number of edges. Everyone know this?
Yes, sir.
Yes.
Yes,
Yes, right. So in tree, the special case is the number of edges. The first point is the same thing we discussed. The number of edges are 1 less than the number of vertices. So the number of edges I can actually write as this thing, number of vertices minus 1, and this will be
okay.
There it is. So there is a direct connection with vertices to the sum of all degrees of the vertices. Number of vertices and the sum of all the degrees of vertices in a tree only, not in any other graphs. Okay, these are few properties, interesting properties to look into. Okay, and there is one more thing, which is finding minimum cost spanning tree. So spanning tree. So what is a spanning tree?
Undirected.
Okay.
Which covers all vertices.
Spanning tree is actually
Subgraph of graph.
Correct. So it is a subgraph of G and it is also a tree. So simply saying, the spanning trees are spanned from a graph. Some graph, which may be tree or may not be tree. Given a graph, I can actually span a tree from that graph. By removing few edges, I can actually span a tree. So those trees are called spanning trees. And every spanning tree is a tree. Okay. And not every tree is a spanning tree, because not every tree are spanned from some graphs. So some trees are defined as a graphs only. So there is nothing to span from one graph. So if the tree is spanned from a graph, then those trees are called spanning trees. And every spanning tree is a tree. Okay, that is what spanning tree is. What we do is, this is a graph. So this is a big graph. So what we do is, from this big graph, we are going to span a tree. So we are going to get a tree out of these vertices by removing few edges. Okay, by removing few edges, we will span a tree from this graph. So that is what spanning tree is. And there is one more thing called minimum cost. So what is this minimum cost? So there can be many spanning trees from a graph. Okay, one example is simply A, B, C, D, E, G, H, and F. So this is a spanning tree from this graph. So this is a spanning tree of this graph. Correct? This is one spanning tree. This is only one spanning tree. I can have one more spanning tree, maybe like A, B, E, G, H, F, C, and D. So this is one more spanning tree. Another spanning tree which is different from this spanning tree. So there can be many spanning trees. Out of these many spanning trees, I have to choose one particular spanning tree which gives me the minimum cost. That means if I choose the spanning tree, then if I compute the weight of that spanning tree, so weight of the spanning tree means weights of each and every edges I have to add. So once I add all the weights of edges of the spanning tree, I should get the minimum cost, which says that if I choose any other spanning tree, if I compute the cost of that spanning tree, that should be greater than this MCST. So this is, in short, we call it as MCST, minimum cost spanning tree. So once I find the MCST of this particular graph, which is the minimum cost spanning tree, any other spanning trees coming from this graph, the cost of those spanning trees will always be greater than or equal to the minimum cost spanning tree. Cost of the minimum cost spanning tree. Understood? That is what minimum cost spanning tree is. And there are, in order to find the minimum cost spanning trees, we have two different algorithms, but both of them give the same answer. Final answer will be same. Whichever algorithm you choose, ultimately you should find the minimum cost spanning tree, or you should find the weight of the minimum cost spanning tree. Okay. So how do we do that? So there are two methods. One is Prim's. So Prim's algorithm, what he does is he actually chooses the least weight in the graph. So there is 3 vertices and there is 3 edges set. So what he will do is he will take the least weight edge. Correct?
Yes, sir.
Am I correct?
Yes, sir.
Yes.
Yeah. Least
Yes,
weight edge, and he will add the vertices of that least weight edge to this TV. So what he does is, so there are 2 least weights. Which one to be taken?
AC.
AC.
AC or DG? Whatever.
DG.
Whichever
Anyone.
you take, ultimately you will reach the same answer. Let me take AC. So AC. So I have taken AC into my TV. And the tree edge I have taken is AC edge. Okay. Now I build the spanning tree. So I have taken A, C, and the weight of this particular tree is 1. Right now it is 1. Now next step, what I will do is I will choose an edge such that it is actually connected to this.
Sorry to interrupt.
Hmm.
Can you please little zoom out?
Little louder.
Can you please little zoom out?
Zoom out.
So we will. Yes, sir.
Okay.
Like this.
Okay. So now what I have to do is I have to choose one more edge that is connected to this edge, which has minimum weight. So now AC edge is there in my graph. Now I have added to my spanning tree. Now with respect to this AC edge, there are 4 edges. So this edge, this edge, this edge, and this edge. And I have to choose the minimum weight edge. So which one is the minimum weight edge? There is AD as well.
AD and CS.
Yeah. Yeah. So you can choose any of it. So either you choose AD or AF, doesn't matter. So I choose AD. So once I choose AD, I will add AD to the edge also. And I will build the spanning tree like this. 4. And this particular thing is also added. And next thing is, so now 3 edges are these 2. So I have to look for the other edges which are connected to these 2 and having the minimum weight. So which one is
D
the
to G.
BD.
GB.
GB, GD, sorry.
GB. DG.
Yeah.
DG. So DG is
DG.
connected to
1.
AD. So I have to add G to the tree vertex set, and I have to add DG to my tree edge. And
Sir, you took AD just because we have to take at least 2 edges.
At least
2 edge.
No, I have taken.
You took AC then AD. What was the
Then
reason?
AD just because either I can choose AD or CF, because AC edge is connected to AB, AD,
AC,
CD, and CF. Okay.
Yes, sir.
So this particular edge is incident to these many edges. Okay. Out of these 4 edges, I have to choose the minimum. So minimum is between 2 edges, 4, 4 I have. So I choose randomly D. You can also choose F.
You get the same answer.
Yeah, same answer. You will get the same answer.
But if I take S, then the next one will be 6, right? I mean, F to D, right?
See, if you take F, the next one will be 5, right?
Yeah, 5.
So this 5 I cannot, this 5 I can choose.
Yeah, but this one you're getting 1, right? Like D to G is 1.
Here is minimum is 1.
Yeah, but the weightage is more in the other case, right?
No. See, here anyway you are going to take this CF.
Yeah.
Okay. In the later part, we will again take CF. So next what happens is, once you take CF here, now we have AC and CF. Okay. These two edges we have in our tree edge. Now with these two, then AD should be taken, not the DF or D, this or this.
Okay, so you have to consider A, C, and F.
Now also we consider AD and AC both. Okay. When I consider AD and AC, I have AB, CD, CF, and all. Once I have D, I have BD, DE, DG, DH. Out of these all
edges are connected to A, C, and D.
D, yeah, A, C, and
all
D.
the previous ones also we have to take.
Got it, sir.
All the previous ones also you have to take. So now this is weight 4, and now this is also added. Like this we proceed. So sorry, weight 1. This is also added.
Then we take DB. This is 2.
Then we take BD. So B comes into the three vertices, and this is BD. So we have to check for all the edges which are connected to A, C, D, G, B. No.
Then we take CF. This is 4.
Then we take CF.
DC,
correct.
no?
DC is 5, right? But CF is 4. So which one is minimum?
Oh.
So that
if we choose, even it was 4 also, we cannot take. Then it will create cycle.
See,
if we take CD
correct.
4, then also we will not allowed to take CD. Right, sir?
Correct. So if I take CD, then that will create a cycle. So that will no longer be a tree. So now CF. So only what I feel is Prim's algorithm is a bit lengthy, or you have to do all these things.
Yeah, I think Kruskal is easier.
Kruskal is a lot better.
Even I feel Kruskal is easier, but there will be a debate, like many people will feel Prim's is easier than Kruskal. So okay.
Then we take GE.
Sir, DB.
Then we take
AB. AB is not possible. GE.
So then we have to take
GE.
GE will do.
GE, sir. Because DF will create cycle, AB will create cycle.
Yeah. Tell me.
Answer GE, right?
And GH.
GH is 7, G is 6. So we will take 6, right?
Yeah, you are completing the tree, right?
Yes, then we take GGH. Yeah.
Correct.
After
so this
that.
is what it will be. Now what happens is, after completing, we will get E as well as H. So 1, 2, 3, 4, 5, 6, 7.
All particles are copied.
1, 2, 3, 4, 5, 6, 7, 8. One more vertex is missing.
So you didn't add F to T.
F.
I didn't add F, right? So after G, I have to add F. B, F. Correct. So B, F, E, H. So BD after CF. After this, it is EG, and then GH.
Yes.
So you see 1, 2, 3, 4, 5, 6, 7. 7 edges are there. So there are 8 vertices. So we need to have 7 edges. So we got those 7 edges. So this is E, which is 6, and this is H, which is 7. So this is what the spanning tree, and this is the minimum cost spanning tree is. So if I compute the weight of this minimum cost spanning tree, it will be like 1, 2, 4, 6, and 7. So this is 8, 10, 11, 12 plus 13, 25. Okay. So this is what the minimum cost spanning tree is. And Kruskal is a bit different, but ultimately you will reach the same algorithm. You will reach the same solution.
Sir, please don't ask to compute a minimum cost spanning tree by Prim's algorithm.
Please don't ask, is it? Did I say?
Yes.
I actually told in the start of the lecture itself.
Yes, sir.
That
there will not be any mention.
You should know at least one algorithm.
Yes, sir.
That is sufficient. Okay. Kruskal algorithm is.
Can
Sir,
you
it
give
is
some
way much easier
important
than Prim's
algorithm?
Important
Sir,
algorithm. See,
sir,
which
can you
one
give
you,
some?
yeah, which one you feel easier, take that algorithm and learn that algorithm perfectly. So Kruskal's algorithm is just you order this edges, graph edges, edge set in order with weight in terms of ascending order. So this will be like AC, DG, BD, 2 के बाद 4, it is AD, CF, AB, CD, and then it will be like 6 DF and GE,
GH,
GH,
EB,
and BE, BE, then
9E.
DH and oh, there are a lot of edges. DH and then DE, and finally we have HF. So once you order these edges in the ascending order of weights, so what you do is you have to construct a tree. So you, in your tree edges, what you do is you take the first edge. So you add that edge to this TE or spanning tree edge. So I say TE only. So I take this edge if and only if it does not form a cycle with the previously added edges. So AC I can add comfortably and DG also I can add comfortably because with 2 edges I cannot have a cycle. So these 2 should be added. Then I will go to BD. So in order to add BD, I will check whether AC, DG and BD creates a cycle or not. If it creates a cycle, I will discard this and I will go to the next vertex, next edge. If it does not create a cycle, then I will add that BD to the tree edges. Like this, I will proceed. So if I proceed like that, this is how the spanning tree looks like. So I will start with the DG, AC. So both of them will be added to my spanning tree. And then BD, smaller one. After 2, there is 4. So I can choose 4. So I can choose AD because it does not create a cycle. Also I can choose CF. It will not create a cycle. Then I will go to 5. So the next weight is 5. So if I try to add this edge 5 AB, then it will create a cycle. ABD will create a
Yes.
cycle. So I will not add it. If I try to add
It
CD,
is also going to create
it
cycle.
will also create a cycle. I'm not going to add it. Then I will move to 6. So weighted 6 is like DF and GE. If I try to add DF to my spanning tree, even this will also create a 4 cycle.
Yes.
So I will not add it.
EG, you can
So I will add EG and then weight 7. So when I go to weight 7, so BE and GH are there. When I consider, if I try to consider BE, then BE, G, D, B again creates a cycle. So I will not add this BE to my spanning tree. But I can add GH because it does not create any cycle. And then if I go to weight 8, so also these algorithms, once you got 6 edges, sorry, once you got 7 edges, so if the number of vertices are 8, once you got 7 edges, then you can stop. So that is your spanning tree. So you see the blue colored graph on the red colored graph, both are same. So the main takeaway from this is whatever the algorithm you know, ultimately you should know how to compute the minimum cost spanning tree and you should know how to compute the weight of the minimum cost spanning tree. Both the algorithms will give the same minimum cost spanning tree. Weight of the minimum cost spanning tree is same in the both algorithms. Okay. Yes. So I am done. So whatever I
Sir,
wanted to
Floyd-Warshall, one example.
Okay. So let us take Floyd-Warshall example. And any other doubts in this particular, before that, any other doubts? I will spend 2 minutes on this. Everyone understood these things, right? Whatever we discussed today.
Yes.
Yes, sir.
Sir, in discuss algorithm.
Yes, sir. Algorithm.
I will discuss the algorithm now.
Can you show this heptagon?
Which one?
A little bit upper.
Sir, Floyd-Warshall
ये वाला
and
Floyd-Warshall पे.
No, it is not upper.
First, please take small one and
Better take the smallest one and we will try to understand.
Yes, sir.
Okay.
Sir, can you give some important algorithm for exam?
Whatever I discussed is what the important one is. Okay. So we have discussed few algorithms, right?
Yes, sir.
So those are the important things. So you want specifically? Nothing like that.
Sir, in discuss algorithm, if a reference node is given, there is no any outgoing edge, then how we proceed, sir?
Can we give an example? Can you give me an example?
Hello, sir.
Yeah, can you give me an example?
In above figure in heptagon, sir, you draw little bit upper. Yes, this one, sir. If reference point is given, suppose D, then how we proceed to find discuss algorithm?
You can only find from D to E, right?
Suppose there is no edge between D to E, outgoing edge, sir.
Okay, then you cannot find. You cannot find anything. The algorithm stops there itself.
Okay, sir.
Okay.
Sir, actually we have 15 minutes only. So for small tree, can you try to apply all the algorithms? Can you please try to apply all the algorithms?
Okay, I will try to apply. But before that, those who are done, you can leave and take a break of 15 minutes and attend.
Can you explain last time? Not explain my confusion about the minimum vertex cover.
Minimum vertex cover, I will deal it. What is the doubt you have?
Like the graph. What? Yeah, sir. So here I thought like if I take the B, then it cover the D, A, and C edges. Similarly, if I take D and E, it will cover all the edges.
No, it will not cover all the edges. It will cover all the vertices. That's it. So you are saying that if I take B, then A is covered, D is covered, F is covered. This is what you are thinking, right?
Yeah. No. A, C, B, F.
Okay. A, C, F,
and D. It's covered.
It's covered. No, that is not the way you should do it. This particular, when I choose B, this is actually covering this edge, and this edge, and this edge. That's it. These four edges it is covering. Okay. It's not covering whole F. So these four edges are covered when I take B.
Yes.
Now there is an edge between A and C. Okay. So even this edge should be covered. This is not covered yet.
Oh, okay. Got it.
Yeah, okay. So for this, I need to have at least A or C into my vertex cover.
Okay.
That is how you come.
Thank you, sir.
Yeah, let's deal with this Floyd-Warshall. So rest of the people, you can take break. All the very best.
No, sir. No, sir. Please explain, sir. Gautam with short 3.
Will it come Floyd-Warshall also?
I don't think so. Okay, let us take a small example. Okay.
So will the question will be asked, or such as that theoretical question will be asked regarding these algorithms? Just as there was a question in mock also, I think, graded assignment key, when we use that algorithm.
So whatever I wanted to discuss, those are the most important topics. Okay.
Yes, sir.
Which one?
Whatever I discussed today, within this 2.5 hours, whatever I discussed is the important one.
You discuss whole topic.
So that is what I said initially also. I discussed completely, but I left a few things which are, it takes time to spend. It takes a lot of time to spend. So those topics I removed actually. So once you go back and see, you will get to know what all topics I have revised.
Can you share these slides?
I will share. So let's say the weight is 2, -1, 4 and 1. What shall we do? Let's say
that will become a cycle.
Cycles are allowed, right? Negative cycles are not allowed.
Oh, okay. No, it's not a tree.
Okay. So this is a small graph we have. We wanted to compute. We wanted to perform the Floyd-Warshall algorithm by computing SP0, 1, 2, 3. So where is the 0, 1, 2, 3 comes is, even though your vertices are named like A, B, C, D, what we primarily do is we give the ordering to these vertices. Like ordering means this is the first vertex I'm going to pick. I'm going to take. And this vertex as the second vertex. And this vertex as the third vertex. And this vertex as the fourth vertex. So the ordering starts from 0. So that is why I have started from 0, 1, 2, 3. So these are ordering of these vertices. Okay. So 0, 1, 2, 3. So what this SP0 means is there are no intermediate vertices.
Means the adjacency matrix, right, sir? Adjacency matrix.
So 0 represents there are no, 0 means there are 0 vertices in between two different vertices. So SP0 is basically an adjacency matrix. Adjacency matrix here, where SP0 means it will, the table shows me from vertex I to vertex J, I have traveled 0 vertices in between. Basically the adjacency matrix also the same thing, right? If there is a direct connection, I will give the numbering as 1. If there is no direct connection, I will give the entry as 0. So that is what this SP0 table means. So this SP0, if I wanted to compute, so I will write it in order 0, 1, 2, 3. When I write 0, 1, 2, 3, it actually means vertex A, vertex B, vertex C, vertex D. So 0, 1, 2, 3. Now SP0 means from 0 to vertex 0, I have to go from 0 to vertex 0 by traveling 0 vertices in between. Okay. So that means, so vertex 0 represents A, B, C, D. From A to A, can I start from A and come back to A? Or simply saying, if there is there a direct edge from A to A?
No, sir.
Is there a direct edge from A to A?
No.
So it will be 0. Okay. From A to B, will it be 0 or infinite? Infinite, right?
Yes, sir. It was infinity, sir.
Yeah.
But sir, I could not understand why
Infinity.
it became infinity. Actually,
See,
0, 0, 1, 1, 2, 2.
Even though you spend infinite amount, you cannot start. Acha, is it infinite?
Yes, sir. Even in practice set 11, week 11 practice set, in the solution it was in infinite. That I actually could not understand in the practice.
Oh, also, sir, there also write infinite in
Yes,
lecture.
sir.
Yes, okay. So here our point is we are starting from A. You started from A. It's not starting from A. You started from A, and I cannot come back to A because I don't have a direct edge or I don't have this loop. So if I
No
had a
loop
loop
here.
like this, then I
Then
can
we
start.
have to remove the loop.
Then you have to
Remove it.
no removing it. We are not considering in this particular course. That's it. If there is a loop, then from A to A I can travel. There is a direct edge from A to A. Okay. If there is no directed, or the infinity refers to I cannot travel from A, starting from A to A by using only one edge. So that is what infinite tells me.
Okay.
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 Like other algorithm, like Dijkstra and other case, it is considered as 0, right, sir? 0, 0, 1, 1, 2, 2. All diagonal part are considered as 0.
No.
I think in Dijkstra, I think.
In Dijkstra, yes. In
Hello.
Dijkstra, we consider it as 0. Correct.
Yes.
Yeah.
Sir, self loop is considered 0, sir. A to A will be written as 0. And whichever is not reachable, that are termed as infinite in Floyd-Warshall.
Yeah, but
actually
in the
that
lecture
should be the like
Infinity only.
convention, but I
that
don't
is the
know here
convention.
in Floyd-Warshall whether it follows the same or something different. That's why I was confused.
See, I understand the confusion.
Sir, A to A does not make sense.
Yeah, A to A, even I agree what you said, but the convention what professor used is what we are going to use. So even infinity or 0, we doesn't get anything from this particular.
Yeah. It is like convention only. How we take it.
It is just the convention you take. So nothing to deal with these diagonal things. We are not going to talk about I start from A and I have to reach A.
Yes.
Something like that.
Yes,
We are interested to find the shortest paths from one vertex to every other vertex, not to the same vertex. So diagonal convention is not that important. Whether it is infinite or 0,
it will be same always. Like in every matrix, it will be same. The diagonal part will be same.
No. Sometimes it may change. Here it may change. You see.
Okay.
From A
Yes,
to
sir.
B
Yes.
to C.
Right.
Sometimes it may change, but
yeah,
the convention infinity or 0 is purely depend on how we take. Sometimes some say we started from 0. Once you started from 0, you are no longer at A. You have moved away from A.
But when you are talking about relaxation, where infinity will
Little louder, please.
Sir, when you are talking about relaxation, so infinity will create problem.
What is relaxation?
When edges are relaxed, means we find minimum among them and relax the edge.
I didn't get what you said.
Actually, sir, from book that I have read, it's saying.
Okay, can you be a little louder, please? Why am I the only one can't hear?
Yes, I also cannot hear properly.
Yes. Hello.
Yeah. Little louder.
Now audible.
Yeah, now okay.
Actually, while finding minimum, whenever we find minimum and we relax that edge, I'm talking about that relaxation. So we use this steps in to deal with this algorithm.
Relaxed or removed?
Okay, I don't know about that relaxation thing.
This is a one YouTube video is use this kind of term, relax.
Oh, I'm not sure about the terminology. I just have to go back and watch that video.
Actually, sir, in book stage also I have read. That's why I'm saying.
Sir, please explain this one.
Okay, you explain, sir. I will.
Because we are waiting for stats also.
Yeah, okay. You are waiting for stats, huh?
Stat class will be started from 8.
Sir, it's a request. So after this Floyd-Warshall algorithm, for the same tree, can you please write down the solution? So we will refer it later. In the same PDF. Yes, sir.
Okay.
With Dijkstra and Bellman-Ford. Yes, sir.
Okay.
Yes, sir. Sir, it will be good, sir.
Okay. So this is what the
Sir, if we consider SP4, then from A to A, it will become 6, sir.
Correct. 7, 9, 8. It will become 8, right? Okay. It will become 6. Correct.
No, sir, we can go to B, D, and A.
Correct.
Then it is not infinite, sir. We can.
Then infinite will be replaced by 6. So we are going to find the shortest paths. So we will keep on update with the minimum value we are going to get. Okay, let us try to compute the.
Sir, this Floyd-Warshall perform, will they ask to perform in the exam, sir?
Did I discuss? Okay, so let us try to get this. So from 0 to 1 within using one edge, can I go? So 0 to 1 means A to B. So the weight of that edge is 2. So like this. So from A to C, I cannot go. That will be an infinite. A to B, I cannot go infinite. So B to A, I cannot go infinite. C to A, I cannot go. D to A, I can go with this particular edge, weight 3. So similarly like this, B to B, C to C, D to D. From B to C, there is an edge weight of -1. Direct edge connecting B and C. And there is a direct edge connecting B and D with weight 1. And there is a direct edge from C to D, which is weight 4. And from C to B is infinite. And from D to B, it is infinite. From D to C, it is infinite. So this is actually an adjacency matrix table where the weights, so when there is a weight comes into the picture, 0 will be replaced by infinite and ones will be replaced by weights. Okay. So this will be SP0. SP0 actually corresponds to the adjacency matrix. And then what is SP1? So when I say SP1, shortest paths using one vertex in between. Okay. And that one vertex is the starting vertex 0. So we have given the ordering, right? So SP1 says that all the shortest paths between vertices, between two vertices, such that 0 vertex can be, so through 0 vertex, between shortest path between two vertices, through vertex 0. So we are going to update, we are going to see, are there any shortest paths when I walk through 0. So I can use one vertex in between. So SP0 means I cannot use one vertex. SP1 means I can use one vertex, which is the first vertex we have ordered in the ordering, which is the first vertex. You can give ordering for A or you can start from C. It doesn't matter. But once you fix the ordering, that will hold for all the complete calculation. Okay. Now
means we have to focus on SP0.
We have to focus on
SP0 for making SP1.
From SP0, yeah, from SP0 you can compute SP1. So what it says is actually you have to look for, so 0, 1, 2, 3 and 0, 1, 2, 3. So you can actually compute from SP0, SP1, or you can actually go back to the graph and see directly. So from this graph, you can see, so using this vertex, there are two paths. There are some paths from D to B, right? There is only one path, I guess. So using A, in between, a new path I found is from D to B. So initially SP0 from D to B, there is infinite. So that means I didn't have a directed, but when I take an intermediate vertex, I have a path, and that is the shortest path as of now. Shortest path using this particular vertex A in between. So once I use this, from D to B, I can travel from D to A and A to B. And the weight of that path is 5. So this particular thing will become 5. If you don't want to use the graph, if you want to compute using SP0, what I look is,
Sir, sir,
huh?
you said 5. So is that the sum of those two weights, 2 and 3?
5. It will be 5.
Yeah, you arrived at that by adding those two weights, is it?
Adding those two weights. So weight of the path is actually sum of all the weights of edges in that particular path.
Okay. Thank you.
Yeah. So now, if you don't want to do that, don't want to look into the graph. Now observe which vertex is coming towards A. So towards A, you look at the column of A. So in the column of A, there is only one real number, which is from vertex D. So from vertex D to A, and you then look at the row D to A and A to B. So there is a path. You update the path. So you look at the column and the row of A, and by looking at it, you can actually update. There is a path from D to B going through A, which is a 0 vertex in our representation. So I can use, so 1 represents, I can use 0 vertex. So this will be updated to 5, and remaining whole graph will be same.
Oh, how did you just come to that so quickly, sir? Remaining will be the same?
Remaining will be the same because in this particular column, I have only one real number. Rest of all are infinites.
Okay.
Okay. So that means from D I can come to A, and from A I can only go to B. Rest of all are infinites.
Okay. Okay.
Okay. From here we can deduce. When I compute SP2, you will get to know.
So how did you get 5, sir?
So 5 because traveling from D to A, the weight is 3, and from A to B is 2. So the weight will be 3 plus 2, 5. And that particular path is actually this. Okay.
What if there is a something intersection of B and A?
What if there is a intersection of
B and A in SP0?
B and A or D and A?
A and B.
A and B. This thing.
Not column wise. From A.
Achha, instead of infinite.
Yeah. This one.
This one.
Yeah.
Okay. Let us not consider B. Let us consider C1.
Okay.
So we'll add one more edge.
Sir, can you please mute everybody?
Okay.
Please.
The disturbance is from my background.
Oh, sorry.
Okay. So I will share this PDF. Okay. So let's say if I add one more edge and the weight of edge is 1 or 2. Oh, sorry. 1. Okay. Now C to A will be 1. Correct. Now when I look at the column, now what I have two real numbers. So C to A is possible and D to A is possible. Okay, that thing I am sure. C to A is possible and D to A is possible. And from A, I can only go to B. There is no other place to go. So that means C to B and D to B. So these two paths will get updated. So C to B and D to B. So here C to B is infinite, and that will be updated to, and this is weight 1 and 2, and this infinite will be updated to 3. Now this will be updated to 3. And this path is D to A, this is 3 and this is 2. And from D to B, I have a shortest path now, which is of weight 5. And this is also been updated. So I only have two paths when I look at the column A and row A. Okay.
Sir. So arriving at this SP2, SP1, is it better to look at the graph or is
it will be better to look at the graph.
Okay, because sorry, I missed in
yeah. For cross checking, it's better. It's always better to look at the graph. So from here, SP2 means I can use two vertices in between. Namely, in my ordering, I can use vertex 0 and vertex 1. So here I can use vertex A and vertex B as the intermediate vertices. So now I am finding the shortest path between two vertices such that in those paths I can have vertex 0 or vertex 1. Nothing else, like not vertex 2, vertex 3. So only vertex 0 and vertex 1 I can have in between. So I want to compute SP2 now. Okay, now I want to compute SP2 where this 0 and 1, both the vertices I can use in between. Now what should I do?
So look at column A, column 1, and see what all edges are incident on 1.
Column 2 and row 2 of SP1 will same.
So look at column 1 and row 1. So if I look at the column 1, so I have a path from 0 to 1 and I have a path from 2 to 3, 2 to 1, and also I have a path from 3 to 1. Correct. So these are the three paths. I have three paths coming from 0 to 1, 2 to 1, 3 to 1. And then I look at the row of 1. So from 1, it is going to 2. From 1, it is going to 3. So 0 to 1 to 3, or 0 to 1 to 2, or 2 to 1 to 2, or 2 to 1 to 2 to 1 to 3. So like this. So 3 to 1 to 2 or 3 to 1 to 3. Okay. So 3 to 1 to 3. Yeah. So 3 to 1 to 3. Correct. So now you have to update the weights now. So 0 to 1. So 0 to 1 is 2. This weight is 2. And from 1 to 3, this weight is 1. So from 0 to 3, now the computed weight is 3. So initially it is 0 to 3, it is infinite. Now we have 0 to 3, the weight is 3. Like this we are going to update. From 0 to 1 and 1 to 2. So from 0 to 1 is 2 and from 1 to 2 it is minus 1. So from 0 to 2 it is actually infinite, but now it got updated to
1.
So the weight will be 1. And similarly we proceed. So from 2 to 1 the weight is 3, and from 1 to 2 it is minus 1. So the path of this is 2. So from 2 to 2 I can actually come back to 2 again using this path. So 2 to 1 and 1 to 2. So it is of weight 2. So from 2 to 2, this is infinite, will change to 2. So like this we are going to update. So update the remaining 3 paths also. So from 2 to 1 it is 3. So 1 to 3 it is 1. So from 2 to 3 is 4. So 2 to 3 is 4. Initially also it is 4. Now also it is 4. So we take the minimum of it. Minimum of 4 comma 4 is 4. So it is 4 as it is. And similarly this is 5, and from 1 to 2 it is minus 1. I will get 4. From 3 to 2 So from 3 to 2, we got 4, but initially SP1 it is infinite, so we will update to 4. And the final path is 3 to 1 and 1 to 3. So 3 to 1 is 5, and from 1 to 3 is 1. So the total weight is 6. So from 3 to 3, so 3 to 3 SP1 is infinite, but in SP2 it got updated to 6. And the remaining will be as it is. Okay, this is how you can compute. Even if you see the graph, so using these two vertices in between, I wanted to find the shortest paths. So C to A to B to C. So this is one path will get updated from C to C. So C is actually 2. So this is C, B, A, D. So from C to C, so C to C you have a path of weight. The shortest path is of weight 2. So you can compute 1, 2 and minus 1. It is 2. So like this. So from D to A to B to C. So from 3 to 2 also it will get updated. So from 3 to 2 also it will get updated. And also there is D to A to B to D. So even this path from D to D is also updated like this. So by traveling in between these two vertices, I will update the shortest paths to every other, from any vertex to every other vertex. So intermediate vertex should be only A and B. So that is what SP2 means. And the final is SP3. So if you have 4 vertices, we will have SP3 table. So SP3 will give us the shortest paths. Why we only take 3?
Uses 0, 1 and 2.
Uses 0.
Vertices 0, 1 and 2 vertices.
Because there are only 3, 4 vertices.
So the shortest path you can have is of length n minus 1. So the path you can have itself is n minus 1. So now itself SP2 will give you all paths of length 2. And also SP4 also it is better to compute, I guess, to check whether we got to a finite value. If there are negative cycles, SP4 will change. Correct. So similarly like this you have to compute SP3, SP4 and everything. So SP3 means you take the third column and the third row and you update, taking the paths like this, and you can update. Okay, I will add this PDF after this session on the portal. You can check the answers if you want, but whatever I discussed is the most important topic.
Sir,
these things, yeah.
Sir, we have to do this exam also.
If
we have to do this in the exam.
If it is given, you have to do.
So there is higher probability that this type of question will come.
There is?
No, just as I was asking beforehand, in mock or graded, there was a question in which it was a theoretical question. Just as you provided the, what we said, instructions or conditions in which theorem will be applicable.
Correct.
So that type of question was there. So we will accept that question.
You can expect those questions because see, these are time
yes, sir, because also the my CT and maths are in same shift. So CT and maths both are time taking and both are in the same shift. That's why.
That we don't consider those things, but we do consider that
yes,
you will be given 1.5 hours, right? So 1.5
yes,
hours for solving some 16 questions or such questions.
Yes, sir. Yes, sir.
So in that 1.5 hours, we will try to estimate. This is our estimation that whether an average student can do this particular paper within 1.5 hours or not.
Okay, and also, sir, one general query: if someone in just a particular subject gets not passing marks in end term, what these are back sum or anything? Because I'm very much scared in maths, because every other subject I'm getting 90 plus, but there it is just
Okay, if
70,
you just
60.
wanted to 70, you wanted to increase your grade, is it?
No, not. I am just a little bit scared this time.
No need to be scared. End-term paper, in regards of graph theory, it was easy.
Yes, sir. Because in mock also, I don't know, it was a competition. In mock also, there was not the graph was not so much tough.
So more or less the paper.
We will expect that type of only.
Right.
Okay. Thank
Sir,
you.
and this Bellman-Ford algorithm.
Session starts. So how long this session will continue?
I think it is done almost. I will take. You can go, and I already said at 7:45 itself I am done. Whatever I wanted to discuss, I am done. This Floyd-Warshall algorithm, I am just computing just because many of you have asked how to compute this.
Sir?
Yeah.
So I had a doubt in graded assignment 11. In the question number 2, it says like, if G is a connected undirected graph such that every vertex has degree at most, for my case it is 6.
Your case?
Yeah, like in the graded assignment. So I had a doubt in the solution. I checked the solution as well, but so it was every vertex has degree at most 6, and the shortest path between any two vertices is of length at most 2. So what is the maximum number of vertices in graph? So according to the solution, the answer is 37. And they made the graph like took one edge, connected it to 6 other edges, and then each of the 6 edges connected it to 5 other edges. So, but there was also this condition like the shortest path between any two vertices should be at most 2. That condition is not fulfilled in that solution.
See, that is actually given that. So if I, in that particular graph, it is not complete graph. It is actually a BFS graph. Okay.
Okay.
It is not the original graph. Okay. So one vertex can have 6, at most 6, right? Once your degree is 6, you cannot have more than 6 in your, if you draw the BFS tree in your level 1, you cannot have more than 6.
Yes, sir.
So this is the maximum possible. We asked you the maximum possible number of vertices, right?
Yes, sir.
And this particular vertex, already it is connected to this, right?
Yes,
and
sir.
It may connect to 5 other different. So in order to have the maximum, it may connect to 5 other different vertices. So we are trying to compute the maximum. Okay. Similarly, like this, this can have 5 more. And this can have 5 more.
Yes, sir, I got that. But what, like for example, if you take any of the nodes in the lowermost level.
Yeah. I understood. This is BFS tree. I am actually telling you this is actually a BFS tree. And this particular vertex is actually connected to only one vertex.
Yes, sir. And the path is, this. So, but then the degree of that vertex would not remain 6, no?
It will be 6. It can have 5 more edges, right? So connect all rest of the, there are 5 more other branches, right? Connect to one particular vertex, not all the vertex. Connect to one particular vertex and take this to here, this to here.
So it would be better if you could label some of the nodes, then I can explain better.
Okay.
So when will you share this slide, sir? Please, with just BFS and DFS, sir.
Like
in which part I will fall? Supplementary contents.
Where we upload every quiz 2 revision session PDFs and quiz 1 revision session PDF.
Oh, okay. Thank you, sir.
Thanks.
It was a great session, sir.
Yeah,
the BFS made with you. Thank you, sir.
Sir, hello. What we have to do in last hours of our exam?
What you have to do in the last hours of after you started exam or before you started exam?
Before means
Before.
when exam.
अच्छा before exam what I would
मतलब
suggest is
लास्ट अभी कौन कौन सा टॉपिक पढ़ के जाए?
पढ़ के जाए मतलब ग्राफ थ्योरी पूरा पढ़ के जाना है और कैलकुलस पार्ट पढ़ के जाना है.
Okay, sir.
That will be better. You will
Sir,
go. You will score
number
more.
of questions.
I already said, right? It will be like 16 or 16 to 17, combining all the subparts. So there will be subparts to each question. So 16 or 17. At most 18. Okay. So from each topic, you can guess like 6 or 7 questions. Maybe from graph theory, you can guess there will be some 6 questions. Like that calculus part, you will get some 6 more. And some from week 1 to 6 you might get some 5 or 6, 5 or yeah. So the weightage of 1 to 6 is very less. So the weightage has been given to you, right?
Yes, sir.
So the more focus is given to week 9, 10 and 11. So 50% is been covered in the week 9, 10, 11. So if you wanted to last में कम पढ़ के जाना है तो just if you are good with graph theory, just learn graph theory well and calculus part well. It will do.
Sir, I was thinking of letting go week 11. So will that be a problem?
No. If you are okay with all the rest of the week 1 to 10, it will not be a problem.
And what about a mock test? माने ओटा दिले हो जावे वो mock test देके फिर ठीक रहेगा ना?
देख के मतलब ऐसे you shouldn't see, you should understand how it is being solved. Okay. मतलब देखने से कुछ नहीं आता है, पहले ट्राई करो कैसा we are doing that, कैसा solution find करना है and understand how the solution is being written. Then I hope you will get a good score.
ठीक है.
Okay.
Thank you.
Yeah. Thanks a lot. And
thank you so much,
sir. The people, yeah, you can leave.
Sir,
and all the very best for your exam. Yeah, I am not leaving you. I will discuss. Okay.
Sir, sir, are you going to discuss some more questions? Can we ask?
No, not particularly. See, it's already 3.5 hours and it is going for 4 hours.
Okay, sir.
Okay. So whatever I discuss for end
small
term,
doubt.
see better for end term, we don't need to have much discussions. For end term perspective, I am done. Whatever we discussed, you can go through that.
Right, sir. Thank you so much.
Yeah, thanks.
Thanks a lot.
Yeah.
Thank you, sir.
Excuse me, sir.
Yeah.
You know, sir, you will just motivate us, right, before the exam. And in stats, we are too much afraid what to do, what not to. And there is not much that type of guidance, what to do.
Stats में?
Yeah.
Stats 1.
Yes, stats 1 में problem हो रहा है, sir.
See,
बता दिया कि 90-12 आएगा, but वो इतना ज़्यादा tough है ना कि सर समझ नहीं आ रहा है.
See, there are some easy topics, right? So I don't know, many people are facing problem in permutation and combination.
But सर उसका तो 5 to 10% आ रहा है, ऐसे मानो कि negligible है सर.
अच्छा 5 to 10% ही आ रहा है.
हाँ, बस वो तो मतलब सीख लिया था, जब तक सीखने लगा कि ओपीपी मतलब सॉरी क्विज 2 तक सीखा उसको और पता चला उसका वेटेज आया 5 to 10% एंड टर्म में, तो उसका तो कोई मतलब ही नहीं है सर.
अच्छा, मेरा हिसाब से whatever the things you learn in the last 3 weeks ना, the random variable and everything, that will be carry forwarded to stats 2. Stats 2 में हम वही डील करने वाला है पूरा.
अच्छा.
Okay. तो बिना वो पढ़ के you cannot see, even if you just pass stats 1, stats 2 में आके you will definitely बहुत problem होगा. Okay, so try learning the most important topics.
और 12th में हमारा था भी नहीं ये सब्जेक्ट.
So that is also facing problem, I guess.
प्रॉब्लम तो सर अब मतलब मैथ्स करके ये सेशन देखकर लग रहा है कि हाँ हो जाएगा, इसका कवर हो जाएगा पूरा कंप्लीट, क्योंकि एक बार इसका पहले भी देख लिया था. आप कहीं प्रीवियस ईयर का यही वीडियो देख लिया था 7 to 12 वीक, जिसमें आपने पूरा बताया था. वो करने के बाद में एक और बार देख लिया तो डबल रिवीजन हो गया. बट अब ना स्टैट्स का बहुत ज्यादा टेंशन हो रहा है सर. उसमें सर ये भी नहीं बताते कि कितने नंबर ऑफ क्वेश्चन आएंगे, कैसे आएंगे.
अच्छा, didn't they give you the weightage and everything? मतलब कितना क्वेश्चंस दे रहे हैं?
अभी तक तो नहीं पता चला सर मुझे.
So this much graph
stats में दिक्कत ये है.
Okay.
Yeah. Can you take Dijkstra theorem?
Huh?
Dijkstra algorithm.
Dijkstra algorithm. See, yes. this is again I am telling you, this is just the BFS. This is not the complete graph. मतलब original graph नहीं.
So you were saying you will connect, for example, 6 1 to 5 1 and then to perhaps 1 1 2 1 3 1 4 1. So but like for in this case only, how will you go from 6 1 to 5 4? You will have to take a path of 3.
See, I just connected 6 1 to 5 1. That's it. I will still connect few. I can connect few more.
So what would be the shortest path to 5, for example, 6 1 to 5 4?
So maybe I will connect 5 1 to 5 4.
So if you connect 5 1 to 5 4, then that means that 5 1 is not connected to every branch of those 6.
May not be. I will connect then, 5 1 to 5 2, 5 1 again, to 5 3. So 5 1 5 2 I will connect to 6 2. Somewhat some things I will do. I will just manipulate here and there. Wherever the shortest path is breaking, I will just remove this edge and I will connect to the other edge.
So still, I don't think the shortest path will remain too.
Shortest path?
Some vertex will remain with the path vertex, not.
See, come up with a proof that yes, this is the remaining vertex. We just ask you the maximum number of vertex possible. ये possible हो सकता है.
So we don't know whether it would be possible, no, sir.
Why you didn't know it is possible?
So how come it?
See, if there is a original graph, this is the original graph. Okay. If I say the shortest path between any two vertices is only 2, if I draw the BFS graph starting from any vertex, I will have only level 2 till level 2.
Yes, sir.
Correct?
Yes, sir.
मतलब कोई भी vertex से start करूं, I have only level 0, level 1, level 2. उससे ज़्यादा नहीं होगा.
Yes, sir.
This is guaranteed. And also we said the maximum degree is 6. Okay. Taking this 2 only into the consideration, without looking, you don't know what the original graph is. So I have given you 6. That is why you are computing. What if I have given you 100?
In that case also, sir, still there would be. You will connect 0 to 100 more edges, 100 more vertices, and then you will connect, if in taking your example only, you will connect each of those 100 to 99 more. So then what will happen to those 99?